we might make a start. For those of you who don't know me, my name's Louise. I'm on the AMOS Melbourne Centre committee this year, and this is the third one of these half-day workshops that the Melbourne Centre has put on. In previous years we've done tornadoes and fire weather, and of course today's topic is about drought. So we're really excited to hopefully present a really nice wide spectrum of people today, covering all aspects of drought in Australia. And I won't talk for too long, but there is a sign-in sheet for those of you who haven't already found it, just at the door here, which is what we're doing instead of having to sign in at reception. So if you haven't done that, please, at the tea break, just pop your name on that sheet. The bathrooms are opposite the lifts, so where you would have come up in the lifts, probably directly in front of you, there's a small passageway. You'll find the bathrooms there, and the doors are unlocked, so you should be able to use them anytime you want. And obviously, in the case of an emergency, we follow all the instructions. So welcome to everyone today, and I won't talk anymore. I'll introduce our first speaker, Ailey. Ailey's a ARC Decorate Fellow at Monash University, and she's very interested in climate extremes, including heat waves and droughts, and she's here to talk to us today about what drought looks like in Australia. So thanks, Ailey.
Well, thank you, and thank you for inviting me here today. So I was kind of asked to speak about what drought looks like in Australia. So I hope this talk will be aimed at the right level. I think some of you probably be a bit too low. Some of you might get something out of it. So I apologise if it's pitched a bit too low. But I thought I'd give you a broad overview of what we think about when we think about drought, and also some of the kind of historical context of drought and some of the processes that we think about, which I'm sure many of you know about. So I was asked to speak about what drought looks like in Australia. Here we go. This is what drought looks like in Australia. You've got your typical images of your, your riverina drylands. Do we have a pointer? Okay. Your riverina drylands. This is Lake Hume during what we call the Millennium Drought. This is a picture of a cattle farm, I think somewhere in New South Wales, during the Federation Drought in the early 20th century. And the dam up there, I'm not sure which dam that is. But that's basically what drought looks like in Australia. So, any questions? I'm joking. So, first of all, when we think about drought, we kind of have to think about defining drought. And this is one of the trickiest parts of drought research, I think, particularly when we're kind of talking about characterising drought, because defining it in the first place is quite difficult because it means different things to different people. This is just kind of an example of that. I just pulled this off the Bureau's webpage this morning. This is, don't need to read the words or anything, but hopefully you can see some of the images here. But this gives kind of an indication of drought in terms of rainfall deficiencies, but over different time periods. So this is the last 4 months, and you see this spatial pattern of kind of very dry rainfall deficits down in the southeast and a little bit in northern Queensland there. Whereas over 14 months, the spatial pattern looks quite different, and Western Victoria starts to pop out as receiving deficiencies. And over 35 months, if you look for that much longer period of time, you see a different spatial pattern again. And of course, you can look at rainfall, but people also like to look at things like evaporation, soil moisture, stream flow, depending again on your application. And so, excuse me, drought research for the longest time has been grappling with this idea of defining drought, I suppose. And people have kind of mulled over it, and really, I would say no one's come up with a fantastic explanation. And these definitions of drought tend to be quite broad because they have to be, because as I said, drought means different things to different people. And some of the difficulties with defining drought are that it's really not a distinct event. It's not a storm, it's not a flood where it happens and stops. Tornado, whatever you want to talk about. It's been defined as a creeping phenomenon and a complex phenomenon. I like that term, creeping phenomenon, from Tannehill, who talked about that way back in 1947. And I know John Wilhite, who's done a lot of work on this stuff in the US, who's kind of a bit of a doyen of drought research, has talked about it as a creeping phenomenon before as well. And it's a creeping phenomenon because it's this complex interaction of a huge number of factors that really has no well-defined start or end. When does a drought start? Well, you can argue about that. And when does it end? Does it end as soon as we get some rainfall? Does it end, as soon as we get well above average rainfall? There's lots of different arguments about that as well. And of course, some of those arguments come down to the fact that the impacts of drought vary by sector, and so those definitions can be very specific to those interest groups as well. And of course, the classical kind of definitions, because of that, have varied, and usually they come up under the broad four banners of what we might call meteorological drought, agricultural drought, hydrological drought, and socioeconomic drought. And I'll briefly go over each of these. Apologies if you've heard this before. So meteorological drought tends to be what a lot of us talk about when we think about drought. So it's generally based on meteorological variables only, so rainfall, and sometimes things like evaporation or an approximation of evaporation, at least, using things like temperature. So broadly defined, we can broadly define it as a period of a few months, 6 months, 12 months, however long we want, of substantially low rainfall compared to normal. And of course, we have those kinds of definitions, for example, like the Bureau uses in terms of deciles, standardised precipitation index, which is one that is coming more and more into use, and things like the Palmer Drought Severity Index, which is quite a contentious one actually, because it tries to incorporate evaporation, but basically does that just using kind of temperature. And so there are questions about whether it's really representative. It was also created using empirical data from the United States, so the question of whether it's applicable worldwide is a good question. And there are lots and lots of other drought indices like these, the Keach-Byram Drought Index, for example. Agricultural drought is generally defined more so in terms of impacts on the agricultural sector, as you might imagine. So this is usually defined by a deficiency of soil moisture, and that's soil moisture to meet the needs of a crop or pasture lands at a particular time. And so seasonality is often quite important when it comes to agricultural drought, in the sowing season or the growing season, things like that. And the definitions are often associated with those direct impacts to plants. So, for example, the permanent wilting point of plants. So agricultural drought, some think of it as kind of occurring after meteorological drought because you need that persistence in lack of rainfall. And agricultural drought can also be called pastoral drought as well if we're thinking about pastoral lands. Of course, hydrological drought, I'm sure a lot of you are familiar with. That's associated with deficiencies in surface and subsurface water supplies, stream flow, runoff, those kinds of things, lake level, groundwater levels as well. If we're talking about extended droughts, things like groundwater can become very important. So this again lags meteorological drought, usually lags hydrological drought, and tends to be longer lasting kind of drought. So these are when we've got precipitation deficiencies inducing these changes at the surface in terms of surface water for generally years to a decade. That's broadly speaking the timescale that we're talking about here. And finally, there's also socioeconomic drought. So people who study drought often look at it in these terms as well. So that's associated with the drought of when a physical water shortage tends to affect society or the economy. So usually we're talking generally larger spatial scales and longer timescales, but it doesn't have to be that way. For example, some might argue that the 2002-2003 drought in South or in Eastern Australia could have been defined as a socio-economic drought because it actually significantly impacted on Australia's GDP in terms of its agricultural productivity. And that was quite a short one. But basically it's to do with supply and demand of an economic product or the health and well-being and quality of life of people. And as I said, the timescale is dependent on those conditions. So when we're thinking about drought and we're thinking about what it really is this complex phenomenon. It's been described as such for many, many years. And that's basically because it has these physical or natural dimensions, but also these social dimensions as well. And people tend to incorporate both, or can incorporate both, into their thinking. Excuse me. And so this complex phenomenon, as I talked about before, if you want to think about time and space scales, this is from a paper by Will Hite back in 2006, or a kind of an overview of what that was. But basically, when we're talking about drought, that meteorological drought tends to be on those shorter timescales, right through to that kind of hydrological drought on those longer timescales. Now, that's in terms of duration of the event, but I would argue, and more increasingly people are arguing, that when we're talking about drought risk and drought definitions, we can't just use things like duration and frequency. We really need to think about spatial extent, severity of any deficiencies, and also that seasonality as well as the frequency and duration. So, just to give a brief overview of drought in Australia, and I'm going to be focusing mostly here on southeastern Australia because this is where most of the research has been over time, so eastern and southeastern Australia. Of course, you're not going to get out of this stuff without reference to Dorothea McKellar. And of course, you know, drought is a big part of our culture here in Australia. And I'm sure you all know Core of My Heart, which is, you know, I love a sunburnt country, land sweeping plains. So it's been in our kind of our vernacular for a long time. So when we think about drought in Australia, though, what does it look like? And I apologise for the black and white images, but I just pulled these from a paper of mine from a couple of years ago last night. So basically, these are what we call seasonal scale drought climatology. So this is more your meteorological drought. So your short time scales drought, and here I've defined drought as the 3 consecutive months in the lowest 10% of rainfall on the left here, which I've defined as meteorological drought, and then soil moisture, which I've defined as agricultural drought on the right. And at the top, in the top row here, for meteorological and agricultural drought, what you see is the frequency in terms of number of events, where events is basically one consecutive period in drought, okay, followed by a break, then another period, okay? And so what you tend to see is across Australia, for the meteorological drought, events tend to last longer in the south and the east than they do in the northwest. And for agricultural drought, they're much the same not last longer, this is number of events, isn't it? They tend to be the same over most of Australia. Now this is all per 11 years or approximately per decade. So for example, in southeastern Australia, we might expect about 6 to 8 events per decade on average. The next row, the middle row here, shows the average duration of these droughts in terms of months in total. And so the average duration, you can see here, is longer for agricultural droughts than for meteorological droughts. We would expect that because soil moisture has that persistence quality in it. And also in terms of drought intensity, basically that follows mean rainfall. You get larger magnitude rainfall or soil moisture deficits where you have larger mean rainfall. So the thing to get from here is that in terms of seasonal scale droughts, we have fewer meteorological droughts in climatologically drier regions, and there are fewer agricultural droughts, but they typically last longer, which makes sense. If we look at how this has changed over time, this is just an example for the Murray-Darling Basin. We did this for a number of kind of major catchment regions across Australia, but I thought I'd show the Murray-Darling Basin. But basically what this shows is the average change over time, averaged over the whole Murray-Darling region of a number of different drought indices which we've defined. That's the same as the events, duration, intensity as I showed in the previous slide. And proportion just means the total number of months in that 11-year period spent in drought. And so you can see that this changes quite considerably over time. Proportion of drought, you can see, was quite high in the early 20th century, and it dropped into the middle of the 20th century and then increased again. You can see changes in the number of events, kind of mirroring that into the mid of the 20th century, and going up again a little bit towards the end, but not as much as in the first part, and that's because duration has increased over time as well. So if we look, and you can see that the mean intensity hasn't changed all that much, although it's increased slightly in soil moisture. So if you look early in the period, you can see that the 1920s and that kind of drier period of the 20s and early 30s was broadly characterised by small number of, more events that lasted shorter periods of time. Whereas if we go forward towards, for example, the 80s and into the 2000s, you can see that we've got a not too dissimilar number of events as in the 1920s, but there are fewer events that are lasting longer towards the latter part of the time series. And of course, this changes and varies over time. Oh, there we go. And so that behaviour changes and is complex over time, and you can see how it matches up to mean rainfall if you look at the annual rainfall in the Murray-Darling Basin over the same time. That black line shows the 11-year running mean, so it basically matches with those ones up there. And you can see how, as I said before, in the 1920s and 30s, that dry period, we had more frequent but shorter droughts, whereas if you look at the more recent periods, and particularly in, say, the 1980s, the dry period in the 1980s and the early 2000s, we've got fewer droughts, seasonal scale droughts, but they are lasting longer when they happen. And so that behaviour and the complexities in that behaviour is something that I'm looking into right now as part of my DECRA project. So that's kind of those seasonal scale droughts. But what about those prolonged droughts or dry periods, that more hydrological type of drought? So we've had kind of three of those that I suppose you would call those kind of multi-year or close to decadal scale droughts over time. So Australia's drought history in that sense, the big ones that have kind of punctuated are the Federation drought, which lasted from around 1895 to 1902, the World War II drought, which lasted from 1937 to 45, and the Millennium drought, which lasted from 97 to 2009, although if you look at some time series in some regions, you might actually think it's still continuing. I should say too that the picture of this Federation drought looks so red and so much worse because it actually only uses data from 1900 to 1902 to make that picture, not from 1895. So it artificially looks worse. So we've had these kind of big, long hydrological droughts in the past, and we certainly have seen them during the 20th century. The Millennium drought was one that happened, and I think Blair's talking about it later, is that right?
Yeah.
Blair's talking about the Millennium drought later, but obviously this is the most recent one that got us all worried here in the southeast. And one of the big questions that's being asked more recently is should we be expecting more of those droughts into the future? Is it climate change, or is it part of natural variability, or is it both? Okay, and so to kind of try and answer those questions, there was a project that happened at the University of Melbourne a couple of years ago, the SEARCH project, where we tried to delve anyway back in time to have a look to see if we could glean any information from what was happening, at least longer than the instrumental record. And this kind of sums up the results from that. So what this shows is kind of wet and dry years, not necessarily drought as extreme low rainfall, but it gives you an idea of those persistent wet and dry years from several sources over time, all the way back to the late 1700s in some cases. So the top one is just a wet and dry index from eastern New South Wales. I think that's based on documentary evidence. The Sydney record, as far back as we can get it. Southeastern Australian, I think that's an instrumental record as well. Now this one here is interesting. This is Lake George lake levels. So Lake George is a lake in near Canberra, I think.
Yep.
And lake levels have been recorded there, not necessarily manually. Some of these were from documentary evidence from farmers. But I think it was H.C. Russell, who was one of the old government astronomers and in charge of meteorology around this town back in the day, put together and reconstructed Lake George lake levels right back to the early 1800s. And so you can see perhaps those times of extended drought and hydrological drought over time with fluctuations in that lake level. And then this bottom one here is from a paleoclimate reconstruction that we put together, a multi-proxy paleoclimate reconstruction comprised of tree rings and coral cores and things like that. And you can see some similarities, you can see some differences. Some regional differences are going to show up. For example, Sydney versus Lake George, either side of the range, is going to be quite different on occasion. But there are also some similarities as well. And you can certainly see periods in the mid-1800s, for example, of kind of prolonged drought for at least a few years. But what about the sleeping giant? And the sleeping giant is something that people are talking more and more about. And this is this thing called mega drought. Okay, so mega drought is not only drought that lasts for a couple of years or a few years or even a decade. It's these droughts that people have seen in, for example, the paleoclimatological record that last kind of multiple decades. They might last, I think there's some that have been shown to, well, potentially shown to last 30 or 40 years. And so there is evidence of that. This is just from one paper showing potential evidence from that. There's a paper that was published by Tessa Vance and colleagues who were looking at an ice core record in Antarctica and trying to link that to changes in eastern Australian rainfall. And what they found in this record anyway were prolonged periods of up to, I think it was 29 or 30 years in very dry conditions associated with that. There's still a lot of work to be done from that side of things and all sorts of other pieces of evidence from the paleoclimate record to show whether that's actually true. But it's also interesting that climate models highlight periods of persistent drying lasting a decade or longer. Some recent work by Andrea Teixeira up at University of New South Wales has shown that even in just a random atmosphere, you can get periods of drought lasting 10 years on occasion. And that's some really interesting work coming out. So just to finish off, I'll just go over some of these drought processes that we all know and love and how they might be linked to drought around Australia. So the immediate causes of drought are often very difficult to untangle, and this is primarily because we don't know this whole thing about drought being a creeping phenomenon with no start and no end. So it's kind of difficult to try and work out what the cause of something is when you can't even define it properly. But of course, there's lots of different factors, and they can probably broadly be summarised as those four that influence drought. So things like sea surface temperature forcing, SST forcing, associated with things like the El Niño Southern Oscillation. Stochastic or random atmospheric variability has been shown to be a recent one. Land surface forcing and also land surface feedbacks, basically adding to drought duration and things like that, and that's an area that's being looked into quite strongly at the moment as well. And of course the big unknown, anthropogenic forcing, and I think Louise is going to talk to us about projections into the future. But of course there's still a lot of unknowns with all of these. And of course then you've got feedbacks and interactions. So you've got, you know, feedbacks of stochastic variability on SST forcing, land surface forcing, and everything else in between. So these things get quite complicated quite quickly. But of course, El Niño Southern Oscillation is one of these big ones, but it can have quite different effects on Australian drought conditions, and these are kind of more meteorological drought conditions. On the left, it shows the typical response to El Niño, but of course, and we can have very, very different responses. For example, 1982-83, these are the 9 months from July to March, July 82 to March 83, and the same period for 97-98. Similar sized El Niño and similar type of El Niño in the Pacific Ocean, but very different local rainfall responses. And of course 2015 is showing some very atypical El Niño responses as well. And of course then there's also a whole heap of other processes, Indian Ocean processes, Northern Australian sea surface temperature forcing, blocking patterns, the southern annular mode, and you can probably name a whole bunch of others as well. And this paper from, I think this one's Murphy and Timble, no, Risby, 2009, basically showing the dominant driver in each season, so summer, autumn, winter, spring, in each, across Australia. So this is the dominant driver of interannual variability in that season. And you can see the SOI, the dark blue representing El Niño Southern Oscillation, red atmospheric blocking, yellow the southern annular mode, and that light blue the Indian Ocean dipole. And you can see that it changes throughout the seasons, and it changes quite substantially regionally as well. And this on the right here just shows how much variance explained in each of these, with most of the variance explained in winter and spring, which is when we tend to see a lot of severe droughts here in southern Australia. And of course then there's the decadal scale stuff, work that Scott Power's done over the years with the interdecadal Pacific Oscillation and relationships between the El Niño Southern Oscillation and Australian rainfall breaking down or strengthening during different phases of that interdecadal Pacific Oscillation, and there's a lot of work being done in that area at the moment. But I will go on because I'm running over time. So, in terms of historical decadal scale droughts, there's a lot of contention about what goes on, particularly with this millennium drought, and I think perhaps Blair will talk about that. But things like more frequent El Niño conditions, positive IPOs, a combination of multiple different reasons, so positive SAMs and El Niño conditions, mixture of Indian Ocean influences and all those different kinds of things have gone in to influence these kind of hydrologic scale droughts in the past. So it's usually not one thing, it's a multitude of factors, and untangling those can be quite difficult. But of course, understanding this stuff on these timescales, on all timescales, is critical. And this is a plot that I've stolen from Neville Nichols very kindly, who sent it to me last night. And Neville's showing this fantastic plot. I've done this, really basic study, but it really shows something really, really important. And I think it's really good to show. And basically what this shows is the relationship between wheat yield in the yellow and June to November rainfall, Australian rainfall, in the blue. And so what you can see over time is that the wheat yield has increased, but you can also see that there are matches in interannual variation. So for example, wheat yield goes down in this year with low rainfall, and here again in 82, 83, etc. And what Neville's shown is that if you take the earlier part of the record, which is shown in red, and that's from 1901 to 1930, and then you compare it to the latter part of the record from 1982 to 2011, what you see is this, and that's a very, very similar relationship that effectively hasn't changed between the year-to-year change in June to November rainfall and the wheat yield. So the slope of that line hasn't changed. And basically, what that's showing us is that the year-to-year relationship hasn't changed. What has changed is it's actually become stronger in recent years. And so basically what that's saying is that practices in terms of wheat yields and things, in terms of agriculture, have improved wheat yields over time because we saw that increasing. But the wheat yields are still showing the same relationship, they're still showing that susceptibility to the year-to-year changes in rainfall over time. In other words, we haven't really adapted to these year-to-year variations in rainfall when it comes to our agricultural productivity. Anyway, that's all I have. If anybody is interested to know more and doesn't have a PhD in this room, we've got 3 projects running at the moment on this stuff. So, or if you know somebody who might be interested, there's 3 projects on this stuff, either run at Monash Uni or the University of Melbourne, so you can come and talk to me about that afterwards. Thank you very much.
We do have time for some questions for Ailey. If anybody wants to.
A very quick, simple one.
Yeah.
The 11-year period that you used for your analysis, what was the significance of that?
The significance?
Yeah.
Why did I pick 11 years?
Yeah.
That was just an example. I picked 5 and 15 as well. But it was just to show kind of decadal scale changes. That's all. So, but yeah, there's no, what's going on here? There was no sensitivity to the time period that was picked. Just basically amplified it. Oops, what is that showing on? Yeah, that one. Cool.
Any other questions for Ailey?
Ailey, back when I was an undergrad, a long time ago, the geomorphologists were always talking about flood-dominated regimes and drought-dominated regimes. Is that still kind of the word they use in
From a geomorphologist perspective, I actually don't know. Peter might know more about that than I do. But yeah, I certainly think people talk about those kind of regimes in the longer time period.
And so in agriculture, that's also, they kind of think that we're going into a wet period.
Yeah, that I don't know. I don't know. You'd have to talk to. But I mean, I think the ones that the geomorphologists are talking about are kind of on much longer time scales, kind of centennial scale, I would suggest. Potentially, but I don't know actually.
you. Thanks very much, Ailey. I'd like to invite Rob Punich to come and present his talk. So Rob's from the Bureau here. I'll just really quickly introduce you, if you like. Rob's part of Rob's a hydrologist here at the Bureau, and he's part of the extended hydrological prediction team, which produces monthly and seasonal stream flow forecasts for Australia, and he's also contributed to the AWRA modelling system implementation, which we'll be hearing about a bit later. What am I doing here? Oh. So thank you.
Yeah. So I had to give a shout out to Uni of Melbourne as well, because some of the work I'm presenting here was done and supported by them when I was working there a couple of years ago. So I was asked to give an overview of soil moisture, just a general overview of, it's obviously important in a drought context of how we measure it, how we model it. So it might be a bit pitched a little low for some of you people who are hydrologists there. So I'll give a little introduction, definitions of soil moisture, what I mean by soil moisture, how we observe it, both in situ and from remote sensing, an overview of a couple of models which are used here at the Bureau, and then look at some examples of data assimilation where we try and combine modelled information with observations and come up with the best sort of prediction. Okay, so as Ali pointed out before, drought, there's a number of definitions, it's a matter of perspective. So again, this is from the same website, which I think she flashed up. I just pulled a couple of quotes from there. So obviously meteorologists have one definition, agriculturists, hydrologists, although we do look at more than just groundwater levels. So there's hydrologists look at the full water cycle. So just an overview, when we talk about soil moisture, we specifically refer to the unsaturated zone. So that's the bit between the land surface and the groundwater table. And if you want to get into a technical definition, for a given volume sample, if you take a sample of soil, there's a certain amount of solid particles, you've got pore space, so it's simply the volume of water for a given volume sample over the total volume, and that's often expressed as a percentage. This is just an example to demonstrate, it's obviously not in the drought here. I've got to point out first, these funny spikes you're seeing in that lower moisture, so this is moisture measured at a field site in the Murrumbidgee about 10 years ago, and they're moisture measured with probes at different depths, so that those red spikes, the lower depth is rising groundwater table, but the point I want to make here is the variation, the temporal variation in moisture. So when you have drought, once you deplete that lower layer, you might have follow-up rain, you'll see a lot of variation near the surface, so it might look good, but it'll take a while to replenish that deeper moisture, and that's really important for agricultural applications. So just a quick comparison here of surface moisture, 0 to 10 centimetres from the Aura model, compared to rainfall deciles. There's roughly, it's kind of qualitatively, there's a bit of a correlation there. You can see the patterns are quite similar, but there's deficits and where there's excess moisture. And so here's another couple of maps. One is from our EHP group, where we look at the past stream flow conditions for the past month. So, and this is for the deeper soil layer, so down to a metre, which we kind of refer to often as the root zone. And that's important for runoff. So you have once your soil profile becomes saturated, there's less, water doesn't percolate as easily, you get a lot of runoff, etc. So you can kind of see the yellow dots there, low flow, generally correlates around Perth and around central Victoria with some of the very dry moisture, and northeast Queensland, and then you've got that little band of wet, above average moisture there, southeast Australia, and there's a few little blue dots there of near median to high flow. So in terms of agriculture, so you need, obviously over the root zone, it's important to have important to have moisture for optimal crop growth. Also useful for irrigation, so if you want to be able to monitor moisture, you want to see it gets to a certain level, if you need a trigger for watering. Also accurate forecasts. It's just popping up by itself, is it?
Yeah, okay.
Okay. So the ability to forecast soil moisture ahead, weeks or months ahead, would be something which is expressed a lot by people, obviously, in the agricultural industry. This still kind of limited in terms of resolution and the quality of some of the data that goes into models to predict soil moisture. So it's ongoing research. As Ali also touched on, land surface coupling feedbacks. So in terms of numeric weather prediction, soil moisture control, sensible latent heat flux partitioning. So if there's more moisture, you get more evaporative fluxes. That's a driver for cloud formation and rainfall. So again, soil moisture is important for initialisation in NWP forecasts. And there's a couple of old studies there that I've referenced which have shown seasonal climate variability related to soil moisture and land surface atmospheric coupling. Okay, so how do we observe moisture? So there's a couple of different methods. So simple one and cheap one is to use probes. We use a reflectometer, sends a pulse down a couple of metal waveguides, and the time it takes to come back is related to the amount of moisture in where the probe's sitting in the soil. These are easy to install. We can log them, hourly time scales and keep them in the field for a matter of years. So this is an example of one of the networks which is probably one of the longest running networks in Australia, the Murrumbidgee catchment there. So it's the AusNet monitoring network. And so you can see Kayapa Creek catchment here is very heavily monitored. And I think it's Adelong Creek, is that right? Yeah. And there's the Yanco region there, which is right abuts the Colliamberley irrigation area. And on your left there's a typical setup. So we've got 3 different depths there four. There's one on the slant there, that's like a surface moisture, 0 to 8 centimetres, and the other 3 are 30 centimetre probes. So we're getting a good characterisation of the over the full root zone there. But you measure the point scale. What does it tell you about landscapes? Calibration. You need they're very sensitive to different soil types. So there's quite a bit of work in there to get good data from them. Okay, so there's also cosmic ray probes, which are a relatively new thing. So they can provide quite large area estimates of soil moisture, up to about 40 hectares. They're quite expensive, and the depth of measurement is quite variable depending on the water distribution. So you might just have a little short depth or up to a metre, depending on where the water is in the profile. And there's a map taken from CSIRO showing where the current network is in Australia. So I think there's a bit of research going on now just to evaluate how useful they are, and they're particularly useful for comparing with satellite estimates of soil moisture, given their large spatial coverage. So there we go, move on to satellite remote sensing. So this is more ideal for, if you want to start talking about operational prediction in the future of soil moisture. So there's a number of microwave platforms, some of the more prominent ones. They're AMSA-E, which died, and it's got its follow-up AMSA-2, which is run by JAXA, the Japanese Space Agency. You've got SMOS, the European one. SMAP is a new satellite, so it's combined active and passive microwave. So the difference there is the SMOS and the AMSA are passive, so they've got a very broad, say, 40 to 50 kilometre resolution. SMAP, with the use of the active radar, you can get down to maybe 10 kilometre resolution. It still might not be ideal for hydrological applications. Farmers want to know what their paddock is like. But the fact that you can get repeat coverage, global coverage over land areas, say from 1 to 3 days roughly, is quite appealing. But the other main limitation is the shallow sensing depth. So you typically only get the top few centimetres. In the case of AMC, you might get 1 or 2 centimetres. SMOS maybe a bit more. So you need a way to take that information and really get it to play nice music. So that's when so there's observed information, so they've got their pros and cons. Then we look at modelling. So there's a couple of, as I said, I'll focus on 2 models. One, AURA-L model, which is developed here in Australia, and a lot of work has been going into it by Adam Smith over there in the team, the AURA modelling team. It's been operational since about 2011 here, Bureau. And so it provides a daily time step of the landscape water balance. And just a brief overview, it's got 2 what we call hydrologic response units, one for deep-rooted vegetation and shallow-rooted vegetation. So at each daily time step, it calculates a water balance, and that water balance, so the change in water store in these soil layers. So you've got the surface one at 10 centimetres, and then shallow one down to about 1 metre, and then a very deep one from about 1 to 6 metres. The change at each daily time step, you'll get either drainage between them, or you'll get water depletion via ET. So whether that's soil evaporation at the surface or through plants. So there's no soil temperature in this model. It's a good sort of just plain water balance. It's being used now quite extensively throughout the Bureau for water accounting and a whole lot of other activities. So cable, I just pulled this out of my thesis, so there's a lot of going on there. Just a schematic to show that, so the cable model, the Community Atmosphere Biosphere Land Exchange model, it's part of the access system. I'm not up with the latest in access, so I know they use joules now, but I think this still has a part to play somewhere. So this is a bit more complex, so you've got vertical moisture movement in the soil layers governed by Richard's equation. Again, you get depletion of moisture via ET. So it's probably not traditionally used as a hydrological model to make predictions. It's probably more in the land surface space where you couple it with atmospheric models and you use it for initializing conditions for forecasting, atmospheric forecasting. So anyway, this is the model that I used for some of the simulation experiments, which I'm going to get into. So data assimilation. So we've got, models are prone to error, uncertainty, inputs and parameters and so on. And obviously observations have their limitations as well. So ideally you want to combine, you've got 2 separate bits of information or 2 independent estimates of the same thing. One, a measurement using a probe or satellite of moisture, a model gives you an estimate. So ideally you want to combine them and try and get the best possible estimate you can. And the key to that, the different simulation algorithms out there, you've got to weigh up the uncertainty in both of those bits of information and combine them to some optimal estimate. It's been shown to have the ability to improve root zone moisture using a shallow estimate. So as I said before, the satellites provide that top few centimetres. And it's been demonstrated using that information, it can propagate and make corrections in the models and improve representation of root zone moisture. So the big challenge really is representing errors, and there's still a lot of ongoing research in that, representing uncertainty on satellite, whether that varies temporally, spatially, and same as with models. Models can be very complex, and it's a big task. This is an example of simulation experiments from a few years ago. It was based on one-dimensional in situ data, so the soil moisture probe out in the field, Kiamba Creek, and I tried to approximately replicate what a satellite, you can't do that, really, but using a 0 to 8 centimetre measure, which is the shallowest, it's still a lot deeper than what you get from a satellite. But nevertheless, assimilate that into the cable model, and you can see here, so by open loop, that just means that the model on its own, and then the light blue there being the observed series, and the orange being the result of assimilating those observations into the cable model. And they were assimilated on a typical timescale of an AMS-3 satellite, so once a day. Now, that first one on the left is that same time series from which the data was sampled, so it's not really it was just more of a sanity check, but this is the one which was more interesting, so it shows that over the root zone, that's purely independent data, and that was able to retrieve something in between the observed and the modelled information. And at the same site, also we looked at ET. So we can see there at the end of the year there, around after day 320, at the site there was evidence there of groundwater supplying excess water for into the soil that was used for ET. Hence you'll see the dark blue, the open loop. So the model by itself didn't capture that, and this highlights another benefit of data assimilation. So the models are bound by their inputs. So you've got just typical forcing, rainfall, temperature, radiation, etc. So it doesn't factor in that groundwater. And by assimilating observations, there may be part of the observation may be seeing that information, and so that can overcome a situation where your model's limited and it doesn't represent a particular process like groundwater. So moving on from the one-dimensional study, this is a remotely sensed assimilation study using AMS data over the Yanco agricultural area. So all those dots there, Y1 to 13, are some of our AusNet stations. And so the AMS are these big black pixels, the 25-kilometre resolution, and the cable was run at 5-kilometre resolution. And we simulated that over a number of years. And this highlights one of the major issues with doing data assimilation is dealing with bias. So obviously you've got two bits of information. The model has its own algorithms and parameters which go into retrieving, the final moisture product from the observation that it makes, and your model's got another set of parameters and so on. So you're going to have systematic biases between them. So you can see the black, the height with a lot of variation there is the AMS-RE, the original. The light colour, light grey, is what the cable, it's output from the cable. And with data assimilation, it's not a technique that corrects for bias. You're looking at differences in anomalies from the mean, from the climatology. So the typical way to overcome this is to apply some kind of rescaling technique, whether you do CDF matching or rescaling the mean and standard deviation. I think there still needs to be a bit of work going into that, or there is ongoing research into that, doing something a bit more substantial, and we can rescale because it kind of works, but it still has its limitations. So this is a summary of the assimilation results from using that satellite information, assimilating it into that top. It's only a 2 centimetre layer of cable model. Now, these metrics here, so anything less than 1 is an improvement. So we sort of set up a normalised R-squared to show how well the improvement how well the assimilated product matched the variability in the observations compared to without assimilation, and then same as with the RMSE. So there's improvement in both of these metrics and representing the variability and in the error. And that ability to improve obviously is much better near the surface. The shallower you are, the more comparable you are to that observation depth, that assimilation depth. And the deeper you go, obviously the more difficult it is to retrieve, because that relationship between that surface and the deep layer is a bit more difficult to represent, especially with the assimilation algorithm. The way it works, you need to represent correlations between errors in the surface and the bottom, and that's another, that can be affected by uncertainties and how do you really define that accurately. So there's a lot of ongoing work in that area as well. But this was, quite encouraging. There's also, I should mention, give a shout out, there's another bit of work showing the simulation of a bunch of different satellite data. It was AMSR, I think it was ASCAT, and Adam, was it SMOS, the European satellite, using the Aura model, and also improved root zone.
Just AMS-RE and ASCAT.
Was it? Okay. But anyway, so that's another independent study using the other model, the Aura model, again, simulating the surface, and we can get a better characterization of that deeper root zone. This is just one of the sites. So those extremes there, so I used the technique, the ensemble column fill. So they're the ensemble extremes of the model prediction. So that's how we define our uncertainty in the model. And that just gives you updated is the model prediction after you assimilate the information in. And that's over that 60 centimetre depth. And that was published last year, which is a really long title there. So, soil moisture is important for land surface state across a range of fields, agriculture, meteorology, and hydrology. Can provide better estimates of moisture than observations or models alone when you assimilate them together. So there's still a lot of work to do. So as I mentioned throughout, defining errors in observations and models, including dealing with biases, how do we really define bias and how do we correct for it. But it shows that it's got promise for, if we want to start doing work towards making soil moisture forecasts, which there's a big need for, it shows it's a valuable technique for initialising models for this purpose. And I want to acknowledge a bunch of different people, obviously Adam Smith and Paul, the Bureau and the group, the HP, Uni of Melbourne, who were collaborators on some of the work I showed on the simulation, Monash, Chris Rudiger, Jeff Walker, who were involved in some of that work. Thanks for your time.
Some questions for Rob?
Hi.
Hi. Thanks for your talk. It's really interesting to see the soil moisture products that I know that's one thing that we struggle to find to use. Just wondering, in terms of your assimilation stuff, how does that compare to the AWAP, the old CSIRO AWAP grids, the soil moisture stuff,
It's another product. I haven't actually compared. We did a sort of qualitative comparison of the Aura with the AWAP, and it compares fairly well. It's I haven't done a detailed study, but it's wet in the right places and dry in the right places.
And is there any evidence that your assimilation scheme, have you looked specifically at kind of drought or extreme dry, I suppose, and see if it does any better or worse?
No, but that's a interesting point, because when you get down to the boundaries in models where you have the wilting point, you can create biases, especially when you do ensembles. You can then bias things, and there's a lot of issues there. But I haven't looked at that specifically. No. Hey.
My question regarding to how the signal from surface propagates downwards to the root zone when you're assimilating the remote sensing products. You mentioned that the benefit probably declines with the depth which will go down.
Yeah.
But just a week or so ago, we had some discussion with IFDEP or whatever, doing observation. Actually, they do show high correlation between surface layer and root zone soil moisture.
Okay.
So the failure here is that due to the model structure or due to the way in which you assimilate?
Well, I can't answer that completely, but I did briefly look at that problem in a work I was doing, and I know that when you have a full profile, there was obviously more coupling between that thin surface, and because when you look at a little A, you're getting a lot of variability, and you're obviously going to have more error. You go further down, you're getting very little variation there. So when there's, say for summer, you've got a drier, deeper zone, and even at the top, if you get a little bit of rainfall and you get stuff bumping around here, there's going to be no coupling there. So I found that when you specify your error correlation or your covariances, you're overdoing it a little bit because you're saying there's correlation where there's not really correlation, and so you may be overcorrecting deeper down. But when you have a wetter profile, you can kind of, there is a stronger coupling there, stronger correlation. But I haven't tested that extensively. But yeah, it's one of those issues that.
Which band are you using for the remote sensing?
Sorry.
Which band?
Which band?
Yeah.
Well, for the And sorry, I just used the product, which was a 25 kilometre product LPRM algorithm from, is it OWA?
Amsterdam.
Amsterdam, VUA, yeah. So the Amsterdam University developed that. Yeah, it was Richard Dejeu and Manfred Owe. Yeah. So it's just a product. I didn't do any fiddling with that. Yeah.
I've got a quick question, actually. It's quite exciting to see sort of remote sensing of soil moisture and stuff. So, where do you see sort of the most improvements to be made? Are the satellites going to get better at being able to observe at depth, or is there still a need for like more and better, probes in the ground, or better assimilation techniques, or what do you see?
I'd be a mix of things, but to me, one of the big ones is downscaling, because that tens of kilometres of one pixel, especially if you want to start doing things for agricultural for applications, you want to really start to downscale, and I think that's one of the big advances we can make, and also the depth as well. But I think, don't quote me on this, but we're hamstrung a little bit by the frequencies we can use. Is that correct? Yeah, there's they could probably get deeper, but especially in the US, there's some frequencies which interfere with different radio with phone signals and
clouds are not an issue with microwaves as such, but as Rob said, there are only certain frequencies that are really sensitive to soil moisture and things like that. And then there's a protected band where there's the optimal frequencies around 1.4 gigahertz, and that gives you between 2 and 5 centimeters sensing depth for the soil. If you use lower frequency microwaves, theoretically you could have a deeper sensing depth, but then the vegetation is in the way.
Yeah. So there's a lot of trade-off. But yeah, downscaling, I reckon, and yeah, that's probably the main one that's doable. Yeah.
Great, thanks very much.
No worries, thank you.
So our next speaker is Blair. Adam? Sorry? Not Blair. That is? Thank you. Maybe I can mute it as well. Adam, does your video have sound? Okay. Oh. So Adam's a senior hydrologist here at the Bureau of Meteorology, and he has recently completed his PhD at Melbourne, which was entitled Soil Moisture Monitoring with Ground-Based Gravity Data. And Adam is going to speak to us today about the Aura modelling system that Rob has introduced to us. So thanks very much, Adam.
So I'd just like to say thanks to Louise and Paul for inviting me to give a talk today. It's a nice opportunity to show some of the work we've been doing in the Bureau for the last few years. So today I'm talking about the Bureau's operational Aura modelling system. My name's Adam Smith, as mentioned. I'm senior hydrologist here. I've been at the Bureau for 9 years. I was in flood forecasting and warning for 4.5 years, and I've been in water resource assessment since then. So in water resources, there's a lot of trade-offs, similar to the data assimilation problem, where different people, so your irrigators, will have different concerns to people doing federal policy for environmental flows and so forth. During the end of 2006, there was which I'm sure Blair will go into with the Millennium Drought, things had got quite dire, and there was a collective agreement to do something about it. And out of that came the Water Act in early 2007, in January, which gave the Bureau powers to collect, hold, manage, interpret and disseminate Australia's water information, which we hadn't done previously. Previously, the Bureau had been bound by the Meteorology Act, so this was a new area of work for the Bureau. We had done some work in water resources previously that Sri was involved with, and the flood forecasting function had been there for a while. But this really ramped up the focus on water in the Bureau, and a lot of people came in around 2008. So historically, water resource assessments for Australia had been done periodically, but by different groups and quite irregularly. So the most recent one prior to the Water Act was the one by the National Water Commission in 2005. And then subsequent to the Water Division being formed in the Bureau in 2008, we had these biannual Australian Water Resource Assessment reports coming out, and we have that's morphed into a new product called Water in Australia that will come out later this year. So to underpin these water resource assessments, the Bureau needed to have an integrated modelling system that captured the landscape in number one there, the surface water stores, so rivers, so forth, groundwater and urban water or water transport systems. And it had to be seamless across jurisdictional boundaries. So what I'll talk to today is mostly that number one is the landscape side of things, but there's work in the other areas that I won't go into. So the modelling system that has been developed through collaboration with CSIRO since 2008 and been operational at the Bureau since 2011 is the Australian Water Resource Assessment Modelling System, and it comprises two main models, the landscape and the river, with the landscape feeding into the river modelling. And around this, these two core models are the functionality that allow us to evaluate performance and ensure that the models are matching observations and so forth with the calibration. And we use these products to produce these Bureau reports and accounts and other things in the middle there which are ramping up. So the modelling system's been recently documented in May edition of the Australian Water Association Journal. So if anyone's interested, they can chase that down and find some more details. We're in the process of writing up a lot of different research and I guess user case studies and so forth for the modelling system that should be published in the next couple of years. And I know at the water conferences in December, the Hydro and the ModSim one, we have an awful lot of conference papers, probably about half a dozen in each on the modelling system. So just going into the models in a little more detail, the landscape model runs over the continent at a 0.05 degree resolution, which is about 5 kilometres, and it's a daily time step model and runs from 1911, January the 1st, through till now. It's driven by the AWAP meteorological data that the climate group set up, and the reason why it runs from 1911 is that's when the air temperature data kicks in for Australia. So the rainfall goes back to 1900. So it's possible to run it from earlier for spin up using climatologies of temperature, but for the moment we're running from 1911. And within each grid cell there's two hydrological response units, so deep-rooted and shallow-rooted vegetation that represents grass and trees, and that's mapped using satellite information. So it's a static map there, but the model's leaf area index, so you do have some dynamic vegetation stuff going on. The river model is a nodal link network model, so Sri Srikanthan and Shishtosh Barua, who are both in the room, lead the work on the river modelling. and it's been set up for the national water account regions around Australia that cover 90% of the water use in Australia. The largest of those being the Murray-Darling Basin. So the nodal-link model on the right there brings in unimpaired runoff from the landscape model and observed stream flows and routes at downstream and models irrigation and so forth. And it gives us an estimate for the losses from the rivers, so what's going into groundwater and into offtakes and so forth. So at the moment we have it set up for these three areas, so Murray-Darling Basin, South East Queensland and Melbourne, which are all national water account regions, and there's work going on to set it up for Sydney and Perth, and then other regions will follow. And you can see from the dots there, which are the stream gauges, that the Murray-Darling Basin's the biggest by far, and was certainly the focus of all the legislation in the Water Act, if you go back and read it. So the river modelling on the Murray-Darling Basin's been tested for inclusion in the National Water Account this year. And that's just a picture of what the regions look like in the 2014 account. So there's a couple up in Northern Australia there, the Ord and the Daly, and then another one's coming on in Queensland as well. But that's just being piloted at the moment. So the modelling system has three different ways you can look at it, three lenses, I guess, of interpreting it. One is interactive, which is how you'd normally think of a model, where you're hands-on and you're using it. Another one is the operational version, which is the scheduled run that runs each day to support products. And a third way of running the model is the calibration, where we do that in a development mode, where we're changing the code and then recalibrating to observations. So the interactive modelling system runs in the IPython notebook. It's, most of the code in the system is Python, with the landscape model coded in Fortran and the river model coded in C. So the notebook runs out of a web browser, and you import some of the modules that do all the background work for you, and then you have this simple object-oriented language where each of those dots, if you hit a tab, it's tab completable, and you can easily explore the code base, and then you run the model. So there's a lot of functionality in there that I'm not going to go into. When you have the outputs, which you can either do from that interactive run, or you just have sitting around from the scheduled run, you can interrogate them a bit, so you can do some visualization. So here we're just displaying the runoff on the left, the gridded runoff, and the rain on the right, that's been aggregated over the month September 2005. So you just have that one-liner to do the visualisation. September 2005 was just a wet period. It corresponds with the plots that Rob showed for his work in the Coomba Creek catchment in the Murrumbidgee, and we're going to drill into that area. So you can kind of see on the map here, there's a bit of blue from the runoff. So zooming in on the same period, we can just change the extent to Murray-Darling Basin, and you can also change to catchments. They're all set up in the system. We have Murrumbidgee River, and zooming into this area, you can see the red box on the left of the runoff coincides with what we're seeing on all the previous plots. So once you're getting down to this level of smaller catchments, you're starting to see the 5K grid resolution of the model. But we can average over any prescribed polygon. So here we've averaged over that Mittagang Creek catchment shown in the previous plot to create the catchment runoff in the top time series and the catchment rain in the bottom one. So that's daily, but again, we can average over time to have monthly or annual as well. So let's see if this works with the cursor. There we go. So this is just an animation of deciles that we can create with the system. So these are calendar years with precip on the top left, that's forcing of the model, actual ET on the top right, gridded runoff on the bottom left, and total soil moisture for the model on the bottom right. So this just shows some of the drought and flood years through the past 100 years, with the 70s particularly wet. So this is something that's readily available at the moment with the work we've done to set up the modelling system. And there's been quite a bit of demand for it from different products, and I'll talk more about it later. Okay, great. So it's all well and good to look at colourful plots and animations, but how can we be sure that the models are giving accurate numbers? So what we've done is there's been a lot of evaluation of the outputs from the model. We have these notebooks like the one to run the model on the right there. That's just a subset of them. So ASCAT is satellite soil moisture, and we have notebooks set up to go to the point of truth of that data and extract it, and the comparison is comparing newer ASCAT data with older ASCAT. And then we can do various benchmarking activities of the model against observations. So we do that against ASCAT, and we have Somerset, which is a remotely sensed ET product, deep drainage, ET flux towers or OzFlux, stream flow for hundreds of catchments, and soil moisture probes down the bottom there as well from the Murrumbidgee and from the Hunter region that Chris Rudiger was involved with. So there's a lot of evaluation of the model. The model is calibrated to 295 catchments simultaneously across Australia, so you can see the calibration catchments in red. And one set of parameters, there's 21 parameters, is used for the whole country. And then that is validated on another 294 catchments, which you can see there. And then we do further evaluation against all those other data sets that are not just stream flow. And you can see from this plot the Köppen climate regions and the coverage of the catchments in those different climate regions. And this just gives an indication of the benchmarking against the runoff. This is monthly Nash Sutcliffe efficiency, so we've just got a couple of the older versions of the model there, 3, 3.5 and 4 against cable and Waterdome. So the calibration against those 295 catchments has been developed to run on the NCI supercomputer region, and we've also got the calibration working with remotely sensed ET and soil moisture across the catchments, so that's catchment aggregated. So version 5 of the model was calibrated simultaneously across 295 catchments using stream flow, the Somerset ET and the AMS soil moisture. And we can also run the calibration locally on a virtual machine, but you can only do that for a handful of catchments, so maybe up to about 8. But it can run a bit quicker if you just got a bit of a localised study you're looking at. And this is just a plot of how the calibration scales with, so in the red there, how the calibration scales with CPUs on the region supercomputer with time per evaluation in seconds of the iterations on the y-axis. So we need to do further testing to see if we're going to hit a limit, but it's looking pretty good performance-wise, and the results are good as well from the evaluation. So The calibration that I was talking on is just for around model development if you're improving the science in the model, and that would be something of interest to researchers. What I'm going to talk on now is the operational product, which is the daily scheduled run. So this runs each day, kicks off at about 3 in the afternoon, and that'll give you today's rainfall. So the rain to 9 a.m. this morning is available in the afternoon. We pick that up at 3 and run the model, and we'll run it from where the AWAP data's last changed. So we've got the most accurate simulation of the past 100 years available every day, and that'll be finished around 7 or so. And then the data is automatically picked up by this Threads data server internally. And there's different ways of accessing that for people in the Bureau. So you've got OpenDAP, web coverage services, web mapping. You can do NetCF subsetting. There's viewers down the bottom, so Diver 2, and data looks like that if you just go on the Threads one. So that's actual ET from 14th of April 2015. So Bureau people can look at this stuff. That's what the catalogue looks like at the moment. So we've got version 4.5 was the main model until recently. We've just migrated to version 5 and previous versions of the model are there as well, 3.5, 3 and 1. So externally, the data is also shared on the research data storage infrastructure on the NCI, the National Computing Infrastructure in Canberra. So it's part of the National Water Data Assets project FJ8. So if people join up with that project, they can access the data. And as part of that data holding, there's also the modelled outputs from the Murray-Darling Basin Sustainable Yields project. So it's a collaboration with CSIRO. And there's also supposed to be modelled outputs from the Bioregional Assessment project as well that the Bureau is doing, although I'm not sure if they're available yet. And my email's incorrect on there, but anyway, the phone numbers are right. So that's a way of researchers getting the modelled outputs and the inputs that are updated each day. And if they have access to the NCI, they would be able to get the data and calibrate the model fairly readily. So more about that later. We're setting up tailored data products for registered users, so different organisations where they can access it for their needs whenever they need via registered user FTP. So we fill in a pro forma like this on the Bureau side for ABARES, and then there's a few mechanisms in the data. The NetCDF files wind up on the FTP site where they can access them, and at the moment they've been looking at something like this, which is monthly runoff soil moisture for different layers, actual ET and potential ET, and they use that for commodity forecasting and a crop production model they've got at the moment. They do seasonal reporting. So we've given them this stuff, and then we've had further discussions with them, and they've refined their requirements, and we'll look to give them the newer product that they're after. Similarly with MDBO, we've been having discussions with them. There's a couple of groups there that are interested in the output. So one of them wants the financial year or the water year runoff for environmental flows. New South Wales State Water Corporation as well are interested in outputs for their computer-aided river modelling over the Murrumbidgee. So that's a operational water management model that allows them to time their releases from dams based on river flows and so forth. And then Digita have been using the deciles for the past 4 months or so as well for the very fast break YouTube video that they do with the seasonal climate outlook. So we supply something like this via Climate with their mapping system, and Digita put their probe data network overlaid on top of it. So you're getting a bit of that spatial information together with the on-ground profile. So people can look at the very fast break if they haven't seen it already. Graham might talk on it later, no? I've been talking to KS as well, Melbourne Water, about giving them maps as well, which doesn't feature here. The New South Wales DPI are after something very similar to the group formerly known as Vic DPI, that are now called Digital because it's easy to say. And I guess I'm just showing here that it's exactly the same map as the other one. So we've got the capability to produce these things nationally and then just carve them up to whatever people need for their particular requirements. So what we've been working on at the moment since July, so all that modelling system work happened since about March last year, when we really ramped it up and turned it into a Python-based system running on a daily schedule in the Bureau. So since July we've been working on a new website that's going to just grab that data automatically that I showed on the Threads server for internal people, and there's obviously a bit of other stuff in between the Threads server and this point, but this website will be coming out in November, so not very long, and it'll have the variables on the left there. So you've got your soil moistures, your runoff, ETs, and precip. And you'll be able to do aggregations over daily, monthly or annual, and we'll have point data, and we'll also have catchment average data on there. You'll be able to download the spatial data, and you'll also be able to download the aggregated time series. And we'll also have deciles on there as well, so the relative information, so how the data ranks in the past 100 years. So this will be available to the general public, and then once people start using this, we're wanting organisations to contact the Bureau and request tailored data products, and we're wanting to establish research collaborations with universities. So next year, once we have the website out, we'll be moving full steam on releasing the modelling system as a community model, guided by the cable approach, and we're looking at a BSD3 type licensing arrangement there. And obviously we need to have a lot more publications so it's citable, and the code base needs some work to make sure that it's completely independent of the Bureau, but this is a key strategy and we're moving towards it. So in summary, the Aura modelling system is a new integrated modelling system. What I've mostly talked on today has been the landscape model. Development continues on the river model, and I'm sure you'll hear more about that in future. We're sharing the outputs internally and externally. They've been used for quite a few Bureau products, which I won't go into now. The website's coming out in November, and next year we'll be looking at releasing the code as an open source project. Thanks. And if you have any more queries, you can send an email to that generic email address, which is the Aura modelling system.
Questions, Adam? Oh, Neville, want to beat you?
It's a terrific amount of work, and it's a great system, obviously. Have you done any market testing? Do you know how many individual farmers, for instance, are likely to want to access it once it goes operational?
No, but Graham offered to do that last week. So, yeah, no, we haven't talked to individual farmers, but there's been a lot of interest from different organisations, state and federal, and city-based water authorities and so forth, even local councils. There's been a lot of interest across the board, and we've only really been asking in the last year or so. So I think once we release the website, we're just going to get flooded with inquiries. There's been some come through the external web that get routed by climate or whatever, where people are after soil moisture information, and I think once they realise that's so readily available, we'll get a lot more feedback. But there's obviously an issue with the 5K grid seal grid cell and how representative that is for a 200 metre paddock. So it's I think the farmers will find it better than
better than going out and sticking
no information. Yeah.
So
yeah, but we're kind of actively trying to avoid pitching at farmers. We'd like to bring the resolution down, but even then, if you're talking 1K or whatever, that's still not paddock scale. So, and we haven't done that work. So.
In terms of going back to 1911 for your modelling systems, you mentioned that vegetation these days comes from satellites. Back then, certainly it didn't come from satellites. So how are you driving your vegetation in the models then, or how are you keeping track of that?
Yeah, so the mapping between the vegetation types, the trees and the grass, is static through time, and then within that the leaf mass can grow. But yeah, it's obviously an area of work that you could do more research into, not with satellites, but but yeah, there's a bunch of different things. We haven't really tackled land use change in the model. That's not something we've done, and we also don't really have management rules and things like that, like a lot of the human factor around water. So there's obvious things there that we can improve with more time and effort.
That's what you want to go, the collaborations with the unis.
Yeah,
the water.
Smart people at the unis, Chris.
And you mentioned the calibration, the validation area. How do you decide it?
The catchments? Yeah, they're all non-nested and they're all unimpaired and they all have a certain length of record and they're all below a threshold of area as well, so you don't have to worry about routing. So there was, selection criteria. There's a rather lengthy report that I think Yongcheng Zhang wrote with Neil Viney on the selection of the catchments. But yeah, they're good quality catchments, basically in summary, both the calibration and the validation. And I've never been completely clear how they decided which should be which, but if you look at the map, it kind of looks like they've tried to pair them. So you've got adjacent ones as calibration and validation. Yeah.
The evaporation data, what's that from?
Oh, it's modelled, yeah. So the AWAC minimum daily air temperature and maximum daily air temperature go into the model, and we use the solar radiation as well that Ian Grant prepares, the satellite product. And yeah, the actual ET is modelled. It's a Penryn ET. Yeah.
And the strategy around supporting community groups to input, I guess, their information into you said it's an independent website from the bottom? Or?
The MCI one?
Yeah.
Yeah, so we're contributors to the MCI. I'm not sure how familiar you are, but with the universities and CSIRO and the Bureau are all partners with the MCI.
Sorry, what's the MCI?
Well, the community model would be somewhat independent of the Bureau, but the Bureau would retain control over the operational version of the model. So I see that there'd be different research versions, and then once a year we'd have a workshop where we'd talk about the recent research results, and there'd be agreement, mostly driven by the Bureau, but with a few key independent researchers about what are the best inclusions into the operational version of the model for that year, and that would get a new version number and go forth.
So that's to get information at a smaller scale, then you'll capture the community input into the model. Is that the idea of
for a smaller scale?
Yeah, so you showed the website that's going to be released next year.
Oh, yeah.
And you talked about a community, another input that was going to be run independently. I think you showed a couple of slides before. So I think there was 3 user groups maybe inputting their soil moisture information.
Oh, was that the deciles for Victoria with the dots and the...
No, it was after that. So I'll talk to you afterwards.
Which one? I'm confused.
That's all right.
Okay. Yeah.
So in your soil moisture buckets, I think you had a shallow one, then one that went down to maybe a meter.
Yeah, that's right.
And then a
6 meters. Yeah, that's a deep bucket.
And so it's a deep bucket. Obviously, in your diagram, you show for the landscape, you've got groundwater down underneath it. It's not explicitly represented, it looks like. But these products that you have available, presumably that would include a drainage flux.
Yeah, totally.
Out of that deep bucket, right?
Yep. So that's shown on the website, and we're currently evaluating that. So that's on the bottom left there, deep drainage, to see whether it'll wind up in the final website or not.
But if I don't want to wait around till the website.
It's like 6 weeks, Kevin, I reckon you're right. Ask Shree, because he's done the deep drainage work.
Okay.
But yeah, it's, a lot of the focus of the modelling in the early days was on the runoff, and we know we've nailed the runoff, and then we've looked a lot at the ET and the soil moisture more recently. Certainly the 10 to 1 metre soil moisture. And then there's other things like the deep drainage, there's LAI that I didn't mention that we could evaluate with satellite products. So there's more things out of the model that people could use, but we need to thoroughly check them all and make sure they're up to our standards before we recommend them being used for various things. So there's been a lot of interest in the deep drainage, which is why it features on the website at the moment. And we've been talking with the groundwater group and so forth about what we're getting out of the model is useful. But groundwater modelers seem to think that an estimate of deep drainage is better than just doing like 5% of rainfall or whatever, which is what they do as inputs to their models at the moment. So
yeah, because there's a big need for that. And you mentioned on the river model, I think you mentioned that there's a linkage for the losing reaches of the stream, but is there no gaining in terms of groundwater feed into the river model?
Yeah. At the moment they're losing. Yeah.
They're assumed to be.
Yeah,
losing.
But you could answer that one if you want. Sure.
Or is there a talk later on the river?
No, there's not. But the river's Shree's area of work. But I think with the off-takes or whatever, you could represent that anyway, presumably. Did you want to comment, Shree?
I think at the moment we only have the losing streams. At the moment, the model can't handle gaining streams. So that needs more work to do because the water table and other things. Normally the water table is low, below the level losing. So gain water, it has to be below the water level. But at the moment we don't have the water table in the model like the present.
But can your off-takes only be positive, or could you have negative?
So even the diversions.
Yeah.
Yeah, that also is possibly taken from the river. Yeah. Other ones can come back to the river system.
Yeah, so at the moment it's like a one-way feed from the landscape to the river kind of thing, and we've done research with CSIRO in the past about having it fully coupled, but it's a rather large endeavour. Yeah. So if there's a need for that, we'll go down that avenue in the future, but for the moment we're just going forth with the landscape is the main piece of work at the moment, and the river's coming along, but it's not there yet.
Well, we might thank you very much, Adam, and thanks to our presenters. We're going to take a 20-minute break now for tea and coffee and biscuits and things which someone set up outside. Just quickly remind you, if you haven't already, to please put your name on the sign-in sheet for us, which is located out there near Okay, so hope you all had a chance to have some tea and bickies. I'd like to introduce our first speaker for the afternoon. Blair's been a climate scientist with the Bureau since '98, and he is a specialist in historical records, in particular extremes. Blair was the scientific coordinator of the WMO's annual Global Climate Statement in 2010 and 2011, and he's also a member of the expert team on climate change detection and indices. He is going to speak to us this afternoon about the Millennium Drought.
Thanks, Louise. Okay, so the Millennium Drought will be familiar to many of you in this room, given it's been part of our lives in the climate sphere for a large part of the last 2 decades. And there are quite a few different definitions of it, which I'll come to a bit later on in the talk. But the greatest duration of it, and also probably the largest effects of it, have been in this part of the world, which is another reason why it's had a fairly high profile amongst a lot of the Australian climate science community, because we're disproportionately concentrated in this part of the world. So I'll start out by talking about the evolution of the drought, what role major climate drivers did and didn't have, because they were only really part of the picture. Look at some of the impacts of the drought and some of the other climate anomalies during the period. So firstly, looking at what we're talking about here, and the Millennium Drought affected only a relatively small part of the continent, certainly compared to, for example, particularly the Federation Drought, as you would have seen from the plots Badali showed in her first talk, where there were big rainfall anomalies over probably 2/3 of the country. The Millennium Drought was confined to really to 3 distinct areas. One being the southeast of Australia, including Tasmania, and especially focused on Victoria. The second being the southwest of WA, where it wasn't really so much of a defined drought, but more a manifestation in the data of a fairly consistent long-term drying trend that we've seen in WA over the last 40 to 50 years. And the third area which showed up quite strongly was southeast Queensland, and that was particularly through the middle stages of the drought, as I'll show in the next slide. In most of this talk, I'll focus particularly on the southeastern Australian part of it, but the other aspects of it are significant and obviously worthy of discussion in their own right in another place and time. As you can see from this map, the period was actually a very wet period through large parts of the country, particularly in the northwest, and that means that statistics like the national area average rainfall are pretty meaningless in trying to define the Millennium Drought, which of course means that such data is freely misused by certain media commentators. So I could probably think of the Millennium Drought in 3 stages. In the first stage, which I speak of as 1997 to 2000, really only a southern Victorian and Tasmanian phenomenon. 1997, which was a strong El Nino year, again, as you'll see from what Ali presented, in most of Australia, the impact of the 1997 El Nino on rainfall was pretty modest, but it did have a substantial impact on Victoria and Tasmania, and spilling over a bit into far southern New South Wales, far southeast South Australia. And then 98 and 99 were dry-ish years, and as I'll show a bit later on, 2000 was a very wet year in a lot of places, but not in southern Victoria and Tasmania. The 2001 to 2006 period was then a period where you had very extensive drought through most of eastern Australia. Included in that were 2 individual severe drought years in 2002 and 2006, both of those associated with El Nino events, interspersed with years in between when rainfall was near to somewhat below normal over most regions. And a recurring theme, which I'll come back to a bit, is that in a lot of cases, long-term drought is not so much about getting a lot of really dry periods. It's about not getting significant wet periods. So here we've got dry conditions through much of Queensland except the far west, through much of New South Wales except for North East and throughout Victoria. And it was during this period that dry conditions in the Murray-Darling Basin were at their most acute. Then the 07 to 09 period, we had continued dry conditions in the southeast and particularly in Victoria, and that leading into the Black Saturday bushfires, of course, among other things. But we saw some recovery further north. In coastal New South Wales, the most acute phase of the drought ended in June 2007 when there was an extremely wet month with a succession of east coast lows, which the Pasha-Bolka storm was the most spectacular manifestation. And that series of events eased substantially the major water shortage issues they had in coastal New South Wales, including Sydney. In southeast Queensland, conditions also improved somewhat. There were La Nina events in the summers of 07, 08 and 08, 09, which brought above normal rain to quite a lot of Queensland. Not quite so much the southeast, but at least things eased off somewhere there. So we've effectively got three stages, and in the southeast, all three of those stages were dry, and that contributed to the extremely long duration of dry conditions. And that stands out here. During the 1997 to 2009 period, looking at southeastern Australian rainfall, we only have the two really bad years, 02 and 06, where southeast Australian rainfall's in the lowest decile. 06 ranked as third lowest after 1982 and 1967. The three others in decile 2, but the real standout here is that in that 13-year period, there's only 1 year which comes in very slightly above normal. That was 2000, and no year made it to decile 7 or above. And in southeastern Australia, it really was a very prolonged period without any serious wet conditions that was a major factor in the water shortages we saw, because as I'll show a bit later on, some of the catchments are particularly dependent on those big years to keep them going. Now, the major climate drivers were part of the story, but certainly not the whole story. So, looking at what El Nino and La Nina were doing, we had El Nino events in 1997, 2002. I'll put 2004 as a question mark. That was a borderline event which was classified as an El Nino by NOAA but not by us. And 2006, and also actually I left 2009 off there. So you did have either 4 or 5 El Nino years in that 13-year period, which is somewhat above the historic frequency. But there were also La Nina events during this period, in 1999 and 2000, quite a prolonged La Nina period there, extending from late 98 to early 01, as well as in 07, 08 and arguably 08, 09. So there's not a massive imbalance in El Nino and La Nina events here. And it's certainly not like, for example, the 1920s and 30s where La Nina events were almost completely absent for a period of 15 years or more. The Indian Ocean dipole is another very relevant factor for the southeast, and a prolonged absence of negative Indian Ocean dipole conditions would also be expected to contribute to dry conditions in the southeast, and we've certainly had some pretty strong positive Indian Ocean dipole events, particularly 1997, and then for much of the period from 06 through to 09, and I think it'd be fair to say the Indian Ocean Dipole was a significant player in the post-2006 dryness in Victoria. But from about 1998 to 2006, there really isn't a lot of substantial Indian Ocean Dipole activity on either side of the spectrum. So we're getting some of the story here, but those two factors on their own wouldn't explain why we went so long without any serious rain in the southeast. It's interesting that when you look at 2000, which was that was a major La Nina year. It was, I think, at the time, the second wettest year on record for Australia, although it's fallen down the ranking list a bit after the 2010-11 La Nina. And we can see here that it was a very wet year over most of the country, and particularly northern Australia, but very little impact in the three major long-term drought areas. In fact, it was a very dry year in southeast Queensland, and generally fairly close to normal in southeastern Australia. So even though the La Nina produced a wet year over Australia as a whole, its impact in fairly localised areas was pretty limited, and the lack of recovery is important here. So also further reinforcing the story of it being more about wet months than dry months. Got here frequency by 5-year period of months in decile 1 Victoria, statewide average. Your expected long-term frequency is 6 per 5-year period. And what we're seeing here is that average across the whole 97 to 2009 period, the frequency of very dry months is actually pretty close to a long-term average. You had, interestingly, you had none at all in the 5 years 2000 to 04. Then you had 12, which is double the expected number in the 05 to 09 period. Quite a few of those were in 2006. But combined, across the whole 13-year period, not much of a signal there. But if you look at very wet months, particularly in the cooler season, it's quite a different story. And on the left, I've got the statewide average for Victoria. And what we see here is, in fact, in the 97 to 2009 period, we didn't have a single month with decile 10 rainfall in the cooler April to October season. The two that are shown in that graph for 95-99 were both in 1995. Even in the warmer season, there are just a couple, February 2005 being one of them. So now when you compare that with the background expected frequency of 6 per 5-year period, you can see that there's been an almost total disappearance of those very wet months in Victoria. And that applies perhaps to a slightly lesser extent at the individual catchment level as well. The Loddon catchment was one that I looked at for some work I was doing a few months ago. And perhaps the most striking statistic here is that when you look at catchment average monthly rainfalls, the Loddon catchment didn't have a single month with 100 millimetres or more of rain between 1993 and 2010. But then had 5 in 7 months, which gives you a pretty good indication as to why there was a flood in Loddon in early 2011. The lack of wet months also affected other areas, and eastern New South Wales was another one that I looked at. Looking at Moss Vale, which is in the southern highlands of New South Wales. Fairly significant area for Sydney's water supply because it's in the wettest part of the Warragamba catchment, and big events on and close to the coastal escarpment can put a lot of water in a short time into Warragamba. Now, Moss Vale, the long-term frequency of 200 millimetre months is about 1 in 15, but they only had 1 in 15 years between 1992 and 2007. And the Sydney catchment is one where these very wet months are important. If you look at total inflows into their catchments, about 40% of all inflows occur in the wettest 10% of years. So if you go for a long period without one of these big months, it just means you're continually drawing down and down on the resource, because in many of these catchments, a normal year of inflows is not enough to meet a normal year of demand, but one big event can set you up for years. The seasonality of the drying is particularly pronounced in the southern coastal wet season. So the map on the right is showing the rainfall deciles in the April to November period since 1996. And we're seeing here a particularly strong signal both in the southeast and the southwest of Australia. Not seeing that much of a signal in Queensland here, but in Queensland that's the drier time of the year. But in most of the southern coastal fringe of Australia, we're seeing a marked decline in that southern wet season rainfall. And the graph on the left indicates that we've only one above average month in that April to August period since 1997. It's worth noting here that the very wet summers of 2010-11 and 2011-12, whilst they obviously had a big impact on annual rainfall in much of southern coastal Australia, had no impact whatsoever on the April to November period. Those winters were still pretty dry. And looking closer at the seasonality over 97 to 2009 period, it's autumn and winter that show the most striking dry signals. Autumn particularly in eastern Australia, and particularly notable in southeast Australia and in eastern Queensland. In winter, a pretty strong dry signal throughout southern Australia, but not much of a dry signal in spring. Something of a dry signal in Victoria and western Tasmania. Victorian dry signal in spring was mostly in the later part of the period. 06, 07 and 08 were all very dry springs, but up until then there hadn't been that much of a spring signal. And summer, generally dryish signals in the southeastern quarter of the country, but not as strong as in autumn and in winter. So looking at a bit more of the picture here, and mean sea level pressure anomalies, and pressure anomalies for the 97 to 2009 period in autumn and in winter, and we've got two quite different patterns here in different parts of the season. In winter, and this is I think probably at least reasonably well known in the broader community, what we have is pretty strong positive pressure anomalies really across south coastal Australia, which can be conceptualised as a southward extension of the subtropical high, leading to a southward retreat of mid-latitude westerlies, and consequently many systems which would previously have brought rain to southern Australia instead passing south of the continent. But autumn, it's not quite such a straightforward story. With generally fairly weak pressure anomalies over much of the Australian continent, although one interesting signal which appears here is southerly flow anomalies over much of eastern Australia, which sort of makes sense because particularly in the earlier part of autumn, a lot of moisture is of tropical origin, and southerly anomalies would be potentially indicating a reduced influence of tropical air masses during that period. And those pressure anomalies in the cooler months are part of the longer term trends, looking at mean sea level pressure averaged over a box 30 to 40 south and in broader Australian longitudes from April to October. And we see a consistent long-term upward trend. It's a trend which is pretty consistent with what climate models say we should expect to see with climate change. And it's noteworthy here that 2015 to date has the highest value on record for this index. So the end of the millennium drought doesn't mean that the signalling pressure has gone away. Now, moving away from the rainfall specifics to some of the water-related impacts. Most of these will be pretty well known. Greatly reduced stream flows in a lot of affected regions, particularly the Murray-Darling Basin during the core period of the drought was probably the highest profile part of the story. And that was basin-wide in the 01 to 06 period. In 07 to 09, it was more focused in the southern part of the basin, but that's probably, from the point of view of the whole basin, is the most significant part of the basin, because depending on how you define it, probably something close to half of the total inflows into the broader Murray system are derived in the high country of southern New South Wales and northwest Victoria. So rainfall anomalies in those areas are particularly important for what's going on in the basin as a whole. As many of you would know, we had major issues with depleted urban storages and associated water restrictions in numerous major cities. As a result of that, we had a lot of infrastructure being built at high cost, some of which has been used extensively. So Perth desalination plants have had a fair workout since they've been built. But quite a bit of the infrastructure that was commissioned during the Millennium Drought hasn't actually ended up having any meaningful use following the rains of 2010-11. That doesn't mean it won't come in useful the next time we have such water shortages. We did have a particularly prolonged period of low Murray-Darling Basin flows, really cutting after 2002, not so much in the early stages of the drought when it was largely confined to southern Victoria and Tasmania, but certainly from 2002 onwards, we'd see the drought really kicking in, and almost throughout the period from 2002 through to 2009, the vast majority of sites in the Murray-Darling Basin had stream flows in the lowest tercile. As I've already mentioned, particularly alpine areas are especially important for inflows into the Murray-Darling Basin. Now, unfortunately, we don't have much in the way of decent precipitation data for the mountain peaks themselves, partly through a lack of long-term observations, and partly because frozen precipitation is very difficult to measure consistently, and a lot of the sites suffer from pretty severe undercatch of snow. But we do find that sites on the immediate western or northwestern side of the mountains in the foothills tend to correlate pretty well with the alpine sites, are a fairly good indicator of what's going on in the alpine regions. I picked out two sites here. One's Batlow on the windward side of the New South Wales snows, and the other's Harrietville at the base of Hotham. And as with the region-wide averages as a whole, we see the lack of wet years as a real standout here. At Batlow, we see very low rainfall throughout the period from 01 to 09. There's all 9 of those years are significantly below average. At Harrietville, it's really the 06 to 09 period that's seriously dry. And 06 in particular was a real standout in at both locations. At Harrietville, 2006 was the driest year on record by about 200 millimetres, which is a lot to be breaking a record by in a site that's got 100 plus years of observations. Now, when we look at impacts on stream flow in Victoria, it does depend quite a bit on what type of catchment you're looking at. And I've got here 3 catchments from different regimes here. On the top left, we've got the Wimmera River in Western Victoria. On the top right, we've got the Thompson catchment on the south side of the ranges in West Gippsland. And in the bottom, we've got the Murrumbidgee catchment on the north side of the Divide, northeast of Melbourne. Now, starting with the Wimmera River, and what we see here is that the flows almost completely dry up during the Millennium Drought. Median post-1996 is about 85% below the median pre-1996, and that's just really a complete absence of significant wet periods in that catchment until we get to 2010, and it's another big year. But in the wetter catchments, the impact of dry conditions, even though the percentage reduction in rainfall over the 13-year period was, if anything, is a little bit higher in the wetter catchments, the impact on stream flow is nowhere near as acute. So in the Thompson, you've got probably about a 15 or 20% drop in stream flow at the sample site here, and in the Murrumbidgee, about a 30% drop. So the drought had particularly large impacts on the drier catchments, many of which saw their stream flows dwindle to little or nothing. Again, these drier catchments, a bit like the Sydney catchment, but in a different way, are catchments where a normal year of rainfall is not enough to sustain normal usage. But whether you get a big year once every 5 years or once every 15 years is pretty critical to the ultimate capacity of that system. Temperatures during the Millennium Drought, consistent with overall warming, were well above normal, particularly for maximum temperatures. In particular, the frequency of high maximum temperatures really took off post 1997, and as one might expect with the dry conditions, that was quite a broad picture across big parts of the country. It's an interesting reflection, actually, that at the time I did my PhD, my main data set was 1957 to 1996, and quite a lot of stations didn't show significant trends for extreme high maximum temperatures over that period, but they certainly do now. As one might expect with a drier period, there's not as strong a signal in minimum temperatures, and in fact some parts of Western Victoria even show a slight cool signal for minimum temperatures over that time, with the increased diurnal range being pretty consistent with the drier conditions. And that shows up pretty well in extremes indices as well, where we see these are maxima, 10-year averages of maxima above the 90th percentile and minima below the 10th percentile. There's a lot of spaghetti here, but the lines you want to concentrate on probably is the dark blue one for Victoria, and we see a sharp increase in the frequency of hot days from about 11% in 1995 to about 14% by the 2000s. But we see after 1980, we see something of a levelling off in the frequency of cool nights below the 10th percentile. And if you break that down further into seasons, that levelling off or even a slight increase is more pronounced in autumn and winter, when the most significant drying has taken place. Now, finishing off, the Millennium Drought has in some ways been largely forgotten about, with the heavy rains of 2010-11, which brought many water storages back to capacity or near capacity, which provides a buffer of several years in a lot of cases. But something that I think has gone fairly unnoticed, at least in major cities, perhaps not so much in the agricultural sector, is that since 2012, rainfall in southeastern Australia has returned basically to Millennium Drought levels. Rainfall deciles for the last 3 years, and particularly in central and western Victoria, we've got quite extensive areas, lowest on record over those 3-year periods, and almost all of Victoria north of the Divide is in decile 1 over that 3-year period. And those are very similar numbers to the ones that we were seeing for example, the 2006 to 2009 period in those regions. So in Victoria, at least, we've seen a return to Millennium Drought levels, but because we're going into that in a stronger position with respect to water supply than we were going into the 2006 to 2009 period, the impacts have not been quite so acute as yet, probably much more so on dryland agriculture, not so much so on water supply and irrigation at the moment. Western Queensland, somewhat separately to this, has had a very significant and prolonged drought, which shows up pretty strongly on this map as well. So just to finish off, we've got the Millennium Drought we've defined as 1997 to 2009. Notably dry conditions through much or all of that period, particularly focused on three regions, southeast and southwest Australia and southeast Queensland, so I should say winter and autumn. The dry conditions particularly pronounced in winter and autumn, but the main seasonal climate drivers are part of the picture but not the whole picture. Longer term changes in air pressure, most likely associated with climate change, appear to be a significant factor as well. And a major factor in the water shortages we saw was a prolonged lack of significant wet periods, especially in Victoria. Okay.
Blair, any questions for Blair?
You showed that for the winter period, the precipitation has basically dropped off under normal. You show the time series of the anomalies here.
Yeah.
Could it be that there has been a shift rather than a loss of the total precipitation, or what does it look like when you look into the anomalies of the food year?
Well, the warmer months for the trend is weaker or near zero in a lot of places. This map shows the four seasons here, and you can see there in Victoria that the spring and summer signals are not as strong as they are in autumn and winter, but it's still a dry signal and not a wet signal. Further north, there are some areas where you're seeing a shift of more rainfall into the summer half of the year. Victoria, in proportional terms, we're seeing a shift into the warmer part of the year, but we're still seeing a decrease rather than an increase in those warmer months. Just not as strong a decrease as we are during winter.
And if the average drops significantly but less significantly in summer, that would indicate that there's some shift happening.
Yeah, of course you're also seeing a bit of a geographic shift, and it's worth noting here that there are several other parts of the world at similar latitudes that see similar patterns. For example, the Western Mediterranean, California, and central Chile all see fairly similar rainfall behaviour. One difference is that what we're seeing within the polar displacement of westerlies is in those regions we also see markedly increased precipitation further poleward. Now, we may well be seeing that in Australia as well, but that's not much use to anybody because it's all falling over the ocean. And in fact, we do see a noticeable upward trend in precipitation at Macquarie Island.
You do in the surface salinity to the south of Australia as well, so it's right before the Southern Ocean. The baroclimatic instability seems to have shifted southwards and eastwards.
Blair, the 97-98 El Nino was dubbed by many as the El Nino of the century and other names like that, and it was right at the start of this period. Would you like to make any comment about it sort of triggering other changes, or have we looked at that much recently?
Not to my knowledge. I think it's possibly in a slightly speculative realm. You get into areas such as what role things like the Interdecadal Pacific Oscillation may or may not have had. And it'll certainly be interesting to see how things evolve as a result of the 15 event, which at least outwardly is showing quite a lot of similarities to 97 early. It looks like you.
I was just going to say, I think Roger Jones at Big Uni's been looking at kind of those step changes for a while now, but I'm not sure if it's had much traction. But his work would be the work to look at if you were interested in that.
But I'm not in a position to make any comment on that because I've been looking at temperatures.
So is there a question there?
Is that Roger's work as well?
That's Roger's work. Yeah, we have been looking at it, but so far we haven't really looked at the relationship of precipitation.
Okay, I missed the last part of your talk. Do we know how the groundwater responds to the millennium drought? And if we say the drought finished, we still say the groundwater still struggling?
I'm actually not familiar with the specifics of the groundwater response. Is there anyone else here who'd like to comment on that? Doesn't sound like it.
We just keep reading that there's a big problem in California.
California is a somewhat different situation in as much as groundwater extraction is a major part of their irrigation system, and for that matter, their urban supply system, which isn't so much the case here. But
great. Well, thanks, Claire. I'd like to introduce Graham Anderson, who is an agriculture climate specialist in DETIJA, which I've heard pronounced for the first time today, which is the Department, for those who don't know, of Economic Development, Jobs, Transport and Resources. Graham leads a seasonal climate risk team, which engages with agribusiness and farmers. And you may be familiar with some of the products like the brake in-use, which Adam mentioned before, and also the climate dogs, which I know I'm a huge fan of. Graham is going to speak to us about some of the work that he does.
Very good, yeah, thank you. Thank you. And thanks for the invite to talk. And we're big fans of climate scientists because we're always asking dumb questions and trying to work out how do we best explain that to people who are very interested in the weather, which is farmers and agriculture. Also welcome colleagues from policy here too, from our Department of Economic Development, Jobs, Transport and Resources, which is the old DPI, is now part of the broader Economic Department. So our insight into drought, I guess for a lot of people when we talk about drought and farming, it's about an experience of drought. So it's not so much the data, it's about what you were seeing and experiencing as you're growing up. So I remember the drought growing up on the farm in 1982, and there was lots going on there. I do remember I got in big trouble because you remember some of you might remember the dust storm that blew into Melbourne. Well, when that blew through our farm north of Ballarat, there was a bit of a panic on around the house because you could smell smoke in all of that dust. So you could only see 50 metres. It was heavy with smoke, so you didn't know if the fire was 50 metres away or whether it was 200 kilometres away. But anyway, there was a panic, and I got in a lot of trouble because I left the back door open. So you can imagine about 3 hours later when we got back home, there was dirt throughout the house everywhere. So I wasn't very popular that afternoon. But those sort of experiences, and it was interesting because, dams filled up with grass and debris and sheep manure, just filled up dams there was so much stuff getting blown across the landscape. Also an interesting story that there's a load of sheep there that were sent off to the market in Ballarat, and my brother's always kept the cheque because he received a cheque for I think it was something like 250 sheep, a cheque for 19 cents for the lot. And so no more sheep went to the market. There was a hell of a lot of sheep disappeared in that drought. So it's really interesting when you're thinking about all the things that were happening then and the experiences that people went through and compare that to what's happening today. And things have got a hell of a lot better, which is terrific. And I guess one of the things when farmers are talking about, seasonal variability, they're always saying we want better forecasts. And if you think back to 82, you could see 2 or 3 days into the future. Now we can see a lot further. El Nino, I don't think was really talked about back then, so there's a lot more discussion around that. So we've improved a lot with the forecasting, and very excited about the big computer you guys are getting and the improvements to Oklahoma and everything else. One of the key things, though, is that it's also making sure that we've improved literacy so that the audience who's hearing all of this discussion about El Nino has some idea of what is it you're talking about and how does it affect our patch. And the other bit is really probably not got much to do with forecasts, is that there are farm businesses that do a brilliant job at managing variable seasons and those cycles of whether it's really wet or dry because of their management and how they set up their business to cope with that flux. And the forecasts add value to it, but some of them do a really good job at that. And I guess the broader debate is we need all three of these happening to get better at managing that variability. Just some context too, I guess, from that, the 82 drought that, it's been pretty amazing some of the changes in farming since then, because we were just looking recently at, I guess, that post-1996, we've only had a couple of years above long-term average rainfall since then, and it's been the warmest 16 years on record. So if you were saying that back in 96, saying you're only going to have 1 or 2 years above average rainfall and we're going to warm you up, how are you guys going to fare? You wouldn't have imagined how actually well agriculture's done. The growth of agricultural production for Victoria has been huge. There's been some big whacks along the way with the 06 drought and issues with irrigation, certainly, but there's been a lot done, and so there's been a lot of new technologies, pastures, management systems, a lot of new infrastructure that's gone in on farms, bigger fodder reserves, better water and all of those things. So better communication technology. Just think that these things, all farmers, what they can get at the end of this now versus what they didn't have access to in 82. These are all really important things. And also say that the communication infrastructure can get a hell of a lot better out there in the bush. So when you're making great products, there's a hell of a lot of people that can't see our YouTube updates because the internet access is no good. So we've got to be mindful of that in this day and age and the importance of that infrastructure. Markets have really changed again, like important one looking at those sheep today. There's parts of Victoria that's pretty dry, but livestock prices are really high. So there's people there saying, oh, well, we'll get rid of the sheep early, but gee, that's a really big, important thing. We've got the growth of red meat industry and exports has really underpinned that. So that's important. Business management for variable years, because in the end for farming, it's around how this affects your income. So that's a really key thing, and often not so much about what you've done in that year, but what are some of those strategic things people have done to handle that variability. And the other thing I think what's been amazing is we've had some pretty dry periods since 82, but nowhere near that amount of dust storm. And if you go up into the Mallee and some of those really sensitive soils, that the conservation tillage, that the ground has always got cover on it. Farmers and grazers all now, there's a hell of a lot done to make sure there's no overgrazing of soils, that stock are managed. And all of those are really testament, but those things weren't happening in 82, but they are happening now. So I think that's really, there's some positive signs there about equipping ourselves to look after the landscape a bit better, because that's often when there's those really big impacts on the landscape is in those sort of 1 in 30 year events. This is just some observations and comments we've had from farmers around drought, is that timing can be a bit cruel, and that's if you've just gone and bought the farm next door and then you suddenly run into 3 tough years, that's bad luck, and that happens. And I know people who have bought land and had a great year and paid it off in a year. So that's a bit unfair. They'd love to have a 3-year forecast before they make a big purchase, but of course that's not possible. The market is really important. So we're sort of looking with dairy farmers a couple of years ago, 2012, there was a bit of a failed spring in southwest Victoria. Milk prices were depressed, and dairy farmers, there was a lot of news about that because they were really hurting. So it's the combo. It's the market price. If your costs are high, feed costs are high, you're not getting much for your milk, and you've got a spring that's finished early. That was really hurting them a lot. So that market thing's a really important bit to consider. There's cycles, I guess, from a business sense. Probably one of the most important things in planning for drought is what you've done in the bumper year. And some farmers make very wise decisions. And there's all sorts of mechanisms, farm deposits and stuff how you can put stuff aside and have income streams for when the inevitable drought happens. There's a lot of people that still don't, have that. But that's getting better. And I guess one thing is that droughts are always easy in hindsight, but they only happen 1 week at a time. So how do you know what's about to unfold? And I think this El Nino, and how it's unfolding is a case in point. That it's never really clear until it's far too late for a lot of farmers. So hence, the aim for the improved understanding of seasonal forecasting. This was a great quote from a farmer recently, just saying, this seasonal forecast, this is like the 3-month forecast. It's a bit like getting access to the minutes of the latest Reserve Bank board meeting, isn't it? And I thought it was a pretty good analogy, because it's saying there's all this data that you guys are reading from satellites, from ocean temperatures, and knowing correlations with different parts of Australia, that you're just saying, here's what things happening, here's the commentary behind it, and really all the Reserve Bank governor does is say, well, for the time being there'll be no movement in interest rates, or they might throw out a signal that there might be room to drop rates. That's probably that's what we're trying to get those farmers to, in terms of saying, listen, that anything can still happen. There's a bit of noise around this, but here's some good commentary on how this situation is panning out for the things that affect your season. So I'm not sure if anyone, is it Andrew Watkins going to be the Glenn Stevens? Someone better tell him that. So our job, I guess, with Dale Gray and Dale Boyd and myself, we've sort of been, we probably do about 100 forums a year, all via request, where farmers and advisor groups are just trying to make sense of seasonal forecasts. And it's been pretty busy this year. And I guess we're sort of in that spot, trying to help with that literacy of all of the good stuff, and trying to improve their confidence and faith in some of the good stuff that's here, and try and make sense of what's a pretty complicated story. And again, we're really appreciative of the help we get from climate scientists. One of the key things farmers tell us, though, that to make a decision on seasonal forecasting needs trust. And it was good when we had discussions like that, and really, it's great to have the aura maps to look at. And one of the things for farmer making a decision is saying, well, yep, they need better scale, like at that paddock level, but also if you're about to make a decision that's sort of in the tens of thousands of dollars, like you're about to spread more nitrogen fertiliser because you think there's enough moisture there in your crop, in your soils to enable that growth, just think, what sort of confidence are you after before you're going to go and make that purchase on the farm? And so we've got people, there's quite a few guys putting in soil moisture probes now. You can do them for less than $4,000, and at least giving them that sort of ground truthing about what's happening in different parts of the landscape. But trust is a really key thing. The other thing with seasonal forecasts is that, and this year's a good one in point for El Nino, people saying, well, I understand there's a huge El Nino brewing because it's in the paper a lot, but what's it mean for our patch? Still trying to work that out. And people are after that rest of the commentary about, so how are things set up for this part of the world, whether you live at Horsham or whether you're in Gippsland. And so I guess that's where that role we're sort of trying to play in that, connecting that there's some good information here that you can trust. We just done some surveys with, we have about 2,800 farmers and advisors across Victoria subscribe to the Break newsletter, and there's 30,000 farmers in Victoria, so we haven't saturated the market by any means, but we're pretty happy that there's a majority of those, I guess, our productive farmers, and they're pretty pleased that out of that commentary that their knowledge on seasonal climate variability is improving, and also to help them make sense of any month at a time with their decisions that they're making. And these are the sort of things that people are, what they're doing, adjusting stocking rates, changing crops, modifying their fertiliser management, adjusting feed, grain allocations, all of that stuff. They do that every spring, but they're just trying to get a bit of a heads up about when suddenly do you get to a trigger point where you decide that there's a mob of sheep here about to go off the farm. And when do you do it before everyone else does? Because you don't want to wait till it's really obvious, because that's when you actually, if you're late to make that decision with everybody else, that's when you actually increase the loss you might make on some of those things. Some stuff here, just we've got a survey that we've done with the Break. This is farmers from 2007, 8, 10, 11 and 14. And there's a few things here. We asked them a question on a scale of 1 to 6, how much emphasis do you place on this particular bit of information when you're making a decision? So a 6 is saying, yeah, that's really important, or a 1 is saying, no, I don't pay any attention to that. So on the left, you can see the 3-month forecast, the bond 3-month forecast. So in 2007, that was, 33% had it ranked as a 5 or 6. And it's good to see that that's up to 60%. So to me, I see there's a bit more confidence coming with that. So that's that literacy thing about, understand a bit more. Making sense of historical climate, that might be where we're backcasting previous El Ninos and that stuff, that's improving. SOI, 28% rated that as being sort of useful for a decision, that's up to about half now. Sea surface temperature maps, really interesting, from 11%, we've got a fourfold increase in that, where these are things that farmers are saying, this stuff is, I'm starting to make sense of this. And all of those bits of commentary are helping me get a bit more confidence about why are they saying there's a signal there for wetter or drier. Just saying it's a signal wet or drier isn't enough. It's actually understanding that commentary, which they think is really gold. And it's okay, they can handle noise, because they do that when they're selling or buying stuff all the time. So it's interesting, we asked for the first time soil moisture, which is pretty obvious, but that's the highest rated one for making a decision. It would be absolute gold if we could get really accurate current soil moisture. So we don't need the forecasting yet, even just starting with exactly how much is there in the top 1 metre would be absolute gold. And for most of the discussions this year, that's really been the key bit. It's that plus the forecast, where farmers are deciding have they got much rain in the bank or not. That's their soil moisture. So we're really looking forward, and I love the work, and it is getting better. A lot of our chats and farmers find this stuff fascinating, the whole climate drivers. There's such a resonation of, they love hearing about Indian Ocean because they see northwest cloud bands, and they've been watching this for years and hearing about things like the southern annular mode, and like that, they're fascinated. They love it, absolutely love it. And it's really interesting that even just a variability point of view and also climate change, they're quite happy to talk about climate change in terms of if southern annular mode is heading south, or if the pressure pattern's getting up. We don't find any resistance to that stuff at all. They're just keen to just tell us what's going on. One of the interesting things we've asked previously about, have you heard of this climate driver, and do you think it affects the rainfall in your district? Because a lot of people have heard of El Nino, but it's a Queensland thing, or it doesn't affect us here. And so that was interesting that from 2009 to 11 we saw improvements in that answer for 4 of the drivers. And just for the brake users, which we asked this question in 2014, that they're perhaps cause and effect, but they're quite excited about this stuff because they realise this stuff is worth getting a heads up on for our patch, for our spring. El Nino commentary this year. What's going on with El Nino? We've been hearing about it for the whole of the year. And what's interesting is that in people's heads when they hear El Nino, they all race off and to different places. We have some farmers go, that's rubbish, there's noise, and others going on. I remember 82. So it's really interesting how, without the good data, you can head off and get yourself down all sorts of tracks. Interesting too here, with the discussion around other things like, is there a bit of southern annular mode pattern to what's sort of going on, and all of that. The Indian Ocean story this year, they've all been things which have really helped farmers try and get a sense about what's the story for Victoria, what's the latest. One of the things which Dale Gray does, and I'll just show this, is using terciles for local rainfall. We call this upscaling, but it's really saying, well, let's look at the previous El Nino events at St Arnaud and just check the spread of, that were decile 1 to 3 or the decile 8 to 9. And this sort of thing, it's pretty crude, but farmers sort of appreciate that because they can sort of see, okay, there's a signal there for El Nino at St Arnaud, but, a third of years were fine. And that's okay. They're happy with that. That's just the general noise. And when you actually run through those years, they actually like to look at that. More detail is better. So they're not actually after the final prediction, they're actually happy that there's noise there. which I find really interesting. And at a place, this is real, they're all leaning forward on their seats and saying that, gee, there's quite a bit of range there. And I think what's important is because there's quite a lot of those years which were fine. And so we've had guys discussing, and agronomists with farmers, and especially like in southern New South Wales, where they're saying they are at that, they've got full moisture profiles in their soils, and they were looking at some of the drier finishes they could have from here, and they're saying, we've not got enough nitrogen out there for these crops to actually grow to potential. So we're actually risking being 1.5 tonne under this year because we're thinking El Nino is absolute disaster. So part of it is about using real known data to help make your decisions and not get swept up in the emotion of it. And also we've got people who have got no soil moisture having a rough time, and they're, that's the starting point for where they are, and actually are having a rough time, So it all depends. That's really important, critical stuff. This is just from discussions we had with some advisors and farmers about 4 weeks ago, and it's just a run through of all of the things that they were doing at the time in terms of their discussions, which shows the level of what they're thinking about managing for the spring. This is with livestock guys, and they're all talking about getting an extra kick for some early nitrogen for what moisture's already there in the soil, getting that out, which stock they've already got ready to go, their feed budgets. There's a lot of pasture management tools, and there's pastures from space and all sorts of things. So there's some really good skills that are out there with that. What most of them are finding a bit hard is trigger points and things like that. This is what came out of that conversation about what can we get better at. And I guess that issue about dealing with uncertain information, when do you make a decision? So if you've got a mob of sheep or something there, you don't, you're wanting to finish them, when's the point where you say, actually, no, I've got to get rid of them early? And again, that's where they're all saying trying to improve their decision making on that's a really key area. Family wellbeing, mental health is a key bit. That's interesting with all of our language too, that there are people that are just in different situations, so more talk of El Ninos and things can really affect them. And some people getting downright cranky about all the talk of El Ninos, like we've had someone suggest that it should be banned, the word, and saying, well, I'm not sure that that's achievable, but it's interesting just some of what they're hearing when we say words, but then where some people go to in their heads. They're obviously thinking something quite drastic. Rain in the bank would be fantastic, and I guess one of the things has been quite a discussion this year, even just about the 7-day forecast, that some farmers are a little bit upset. Just about, I think, trying to understand the level of skill in a forecast, and especially when you've got a complicated rain band coming across. And I know there's a lot of work here to say that, we think maybe this is a 15 mil event. If it doesn't happen and they've just spent $40,000 of putting nitrogen out there, they're pretty cranky. And in their heads are just saying, well, I understand cut-off flow systems can be really complicated, so do we need something that goes along with this forecast? So just this event, we've got some problems with this event, it could be this big. So I think we've all got to work out how do we help them understand that they can cope with uncertainty, they just want to know what it is. And that changes. Not every 7-day forecast is the same, so we appreciate the challenges that forecasters have. And if you're wondering why farmers get a bit sensitive sometimes, just imagine your celery went up and down according to SOI. Right? So the celery office index or celery oscillation index. So often when people don't show the same enthusiasm for El Nino, there's a good reason, So that's the emotional part that comes with this. This year it's been interesting too. Godzilla El Ninos, and people getting quite excited about the big El Nino. And it was interesting being interviewed by a journalist a few years ago who was very excited and saying that what if we got 3 in a row, And it was then I realised that actually, from a media point of view, the stories about the sensation and how bad can the bushfires be, and it's just a disaster. And that stuff for someone who's just bought the farm next door and is worried enough anyway, doesn't actually help them much. And the comment about, don't talk about El Nino, they're saying it's okay to talk about El Nino, but on the way to the commentary and discussion about, well, how are things shaping up to here, and that, helping make sense of this. So the equivalent would be, if just the Reserve Bank was just talking about Greece all the time, but didn't mention any data about what's happening in the Victorian economy, that's what they're after. So, okay, talk about Greece, but talk more about what's actually happening here as well. So I'm not sure if that works or not. The other thing that farmers have liked, Dale Gray puts out a bit of a table run of some of the different 3-month forecast models, and there's 11 there. We call it a footy tipping sheet, but basically it's just another thing too that provides a bit of a thing about, well, how many models out there have got a bit of a drier pattern for this part of the world, and that's certainly, so once suddenly, more than 3 or 4 start lighting up, there's something there. So that works for some people, that sort of approach. Rain in the bank, the soil moisture probe stuff, so that's really hitting a chord, and you can sort of see there, this is for the circles where, soil moisture was at this time last year compared to this time this year. That stuff is really critical for farmers when they're looking at strategies for the spring, because it's, okay, whatever might happen with rainfall, but we're starting from behind. So that's important. So, and also one of the things, these are probes that are sort of, they start from 30 centimetres, so they're out in the cropping paddock, the 30 centimetres down to a metre. So they're pretty valuable information. Get measurements at every 10 centimetres. And farmers can even see that in summer, when there's a rainfall event, if there's summer weeds, they can actually see the zigzag lines of summer weeds taking that moisture away. So that's why they're out pretty quickly spraying weeds, because they're getting very good at conserving summer rainfall that's for use in the growing season by the crop. So really good adaptation to keep that happening. So you only need 3 or 4 plants in a square metre, and once you see that zigzag, they're out there spraying it pretty quick. So yeah, soil moisture stuff's all very handy. So this is how it, I guess, unfolds in a farmer's mind. At any point they know what rain they've had, but hopefully know what rain is in the bank. There's the 7-day forecast, then the 1-month outlook or longer, and we're looking forward to those multi-week forecasts that are coming. And then there's those longer-term trends about, well, autumns are being, a lot less reliable now than they were. A lot of our southern farmers would say drier winters has actually been useful for them, if you're a dairy farmer. But make sure that the spring's good. So that's all we've got, and then the big part for farmers is making the most of what they've got actual control over, which is that decisions, and some do that a lot better. Key points in the year, production, known benchmarks and thresholds. About once we get to this point, we pull the trigger. This is what starts to happen on those farms. That's what the better managers are doing. So, and that business bit, which is essentially about managing that salary office index issue about how do you set up your strategy before you've got to a drought, so that you actually know you're going to be fine because you've got income from other streams. And I'll just finish with the question really, which was, we talked to farmers about, if they've got an animal that's a bit sick on the farm, they're on the blower to the vet, and they're using the latest veterinary science to diagnose the issue and treat that. But it's really interesting. Think about who do farmers speak to when they're getting something as important as their weather and their seasonal outlook information. And do we know? Because it's really interesting. When you think of something that's so fundamentally important for agriculture, I'm sort of a little bit scared sometimes what I see people using, especially for seasonal forecasts, and thinking, and I guess on the age of the internet, you can get any website you want, and if it looks good, then that's great. But it's saying, do you understand where that data's coming from and where that's got? And I think there's room for us to improve that, because we'll improve the trust in actually making sure you're getting this stuff from the right source and you're understanding what these maps are and what the data's coming from. So I guess that's part of our challenge of how we get better at that, because we're going to need to get better at it, and we've got all the technologies that we can. So taking it all from global to local. So hopefully that's covered off my bit. Thanks, Louise.
Yep.
Good.
Quick question for Graham. Whoa. Rob, I think might have been first.
Thanks. That is a really interesting coverage, I think, of the perspective that the agricultural sector's got for seasonal. You mentioned climate change just a couple of times. I guess the question is there appetite for information about climate change? Is it seen as something that's potentially useful for farmers? And if so, in what way? And how would they appreciate that? How might that information be useful for them?
The words climate change and the language has been really almost bipolar because of the political discussions that have been happening in Australia. And there's a lot of farmers that don't want to hear about climate change. But if you start talking about pressure patterns, autumn drop, temperature trends locally, anything to do with trends locally, they love it. And it's interesting even, we show some of the modelling about why Southern Australia might have a different signal in the climate change models than Northern Australia. And that's the first time a lot of farmers have seen that because they don't like being told a prediction that your rainfall is going down by 10% in the next 70 years. But the story of how the models work and saying, well, if the world warms up, the tropics expands from the equator and everything gets nudged towards the poles, they go, yeah, okay, get that, because I've been watching those fronts slipping south and, you've got some data there on the pressure pattern getting stronger. Geez, we've been noticing, so they're pretty observant, and if you're actually laying that trail of just trend stuff, they rank that very highly. And then there's the discussion about, well, what's behind this trend and does it continue? What bit's variability and what bit isn't? And I guess that's what we tend to talk about, that ENSO and iodine, all these seasonal variability continues, but there's a couple of things. Is there anything that's a bit different? And the temperature one we probably have undersold. I think in 2011 we had a survey of over 1,000 Victorian farmers and asked them, do you think your district's getting warmer? And only 1 in 4 thought their district was getting warmer. And it's interesting, even if you repeated the last 100 years of variability, which we're unlikely to do, but even if you did and you had it 1 degree warmer, the issue of drought or pinched seasons or all that is just those two alone would be more so without actually adding, pressure pattern changes and other things in there. So I think it's, we don't use the word climate change a lot. We tend to have it all in there as it's, this is what's happening in the 17 kilometres above your head, I often get asked, do you believe in climate change? And Dale Gray, we get asked that, and our answer is, well, the atmosphere couldn't care less about what we believe. It's just about the physics of the ocean, the atmosphere. And certain media commentators will make a great living, stirring up scientists and boffins and lefties and that stuff, and say, farmers, you're actually dealing with what the weather is. That you've got a lot riding on this, so it's good to tap into a trusted source. So that's sort of the discussions we have on that. So trends is good.
So your department and farmers in Victoria have a lot to look at. That's the message you've got. A lot to understand. Well, I'm going to add something more. Rainfall in Victoria, the relationship with ENSO is there, but it's a bit flaky.
Yeah.
But there are many parts of the world where it ain't flaky at all. It is basically, you have an El Nino, you have a drought.
Yeah.
PNG, Indonesia, it's very, very rigid relationship.
Yes.
And the PNG Prime Minister, I think last week, was saying they're looking like they're going to have a record drought.
Yeah.
And it's already, the fires are on Sumatra.
But someone who was there only 2 weeks ago in the room, yeah.
So it has to affect markets. And I've always thought that perhaps the most biggest influence of El Nino on Victorian farm economies is going to be the effect through the markets in areas where the relationship is much stronger than the climate in Victoria.
Yep.
So how do you get that message out to farmers, and how do they assimilate that sort of information quickly?
Yeah, well, it's a bit tricky because because we're so reliant on export markets, a key part of good years for us is that there needs to be failure somewhere else to be increased demand and better prices. And I remember speaking to some Esperance farmers a couple of years ago, big wheat farms there, and they had 2 years in a row where they had the same tonnage of wheat left the farm, and 1 year was a break-even year, and the other year was their record financial year, and all to do with the global wheat price. That is not really out of their, it's out of their control. They can do some hedging and stuff, but largely that is such a big thing that determines that impact, that financial impact. But it's looking at the American stuff is a really key one this year, and there's big weather happening all over the planet, and heat waves and what's Ukraine doing and all that stuff, and so they're all watching that, and it reacts quickly. But I'm not sure that explanation of, it sounds like you could write a nice little summary for us, Neville, about where those secure areas are, and especially where they affect some of those global commodities.
Quick one, Mary, I think might have been next.
If you were given a big pot of money, would you put it into improving the NBN, improving the seasonal forecast, or that 7-day issue that you mentioned during your talk, or maybe something else? And you don't have to choose kind of one, but give us a feel for where you think things should be heading.
Yeah, well, I think that that infrastructure is really critical, because all of the good stuff you guys are doing, if there's a whole bunch of people there that if it's taking too long to download, it's not, so that's a key one. But I think the climate stuff, climate change only turns up, in 7 days at a time too. So it's that connection of forecasting from, the 3-day stuff, which is high confidence, and the 7-10-day, the multi-week stuff out to the 3-month, and then that broader trend. Somehow it's sort of the ability to connect all of that, and faith in it. So I think you've got faith in the shorter forecast. We're just trying to build confidence in those ones heading further out. And I think one of the things is farmers, they're amazed at how much measurement is taken of the planet now. That, in terms of all of the Argos that are out there and the satellite stuff,
So are we.
Yeah, and I think part of just saying, guys, this is a pretty amazing time to be alive. We've got all this stuff here that in the 80s they didn't have, in terms of looking at weather and weather patterns and all that. So we're just going to make sure they're getting to see that and trust it, really. Yeah.
Thanks, Graham. We might have to leave it there because we're running a bit behind now.